Have you ever wondered what lies beyond the stillness of the night sky? Imagine a moment when the familiar walls of your mind begin to shift, and a new sense of possibility awakens within you. In the next few minutes, I will guide you through a gentle journey that uncovers how the very fabric of space and time can inspire you to rewrite the story of your own life. Picture the universe as it once imagined by early thinkers, a vast expanse of empty space that simply exists, waiting patiently to be filled. In that ancient view, space behaved like a silent stage, unchanging and indifferent to the objects that moved across it. It was a grid stretched in all directions, fixed and eternal, where a meter meant the same everywhere, and a straight line never bent. This comforting picture matched everyday experience. When you walk across a room, the floor does not stretch beneath your feet, and when the sun arcs across the sky, the backdrop appears steady. From this perspective, motion belonged solely to the actors, while space itself remained a passive container. At the same time, time was thought to flow like an unvarying river, ticking away with perfect regularity for every observer. A second on Earth was assumed to be identical to a second on a distant star, and clocks everywhere were believed to keep perfect harmony. This absolute time provided a universal rhythm that seemed to govern all events without ever being swayed by speed, mass, or direction. The two ideas, fixed space and steady time, combined to form a neat, orderly picture of the cosmos that felt almost obvious. It allowed early scientists to measure speed, predict paths, and describe motion with confidence, because both the stage and the metronome were thought to be immutable. When you rest inside this simple model, you may feel a deep sense of stability. The ground beneath you feels solid, the clock on your wall ticks without surprise, and the world appears predictable. This feeling of certainty can be powerful. It reminds you that you, too, have a foundation upon which to build your dreams. Just as the ancient view gave early physicists a reliable platform, your own core values can serve as the steady ground that supports every step you take. When you recognize that a reliable base exists, you can focus your energy on the actions that move you forward. But beneath that calm surface, subtle questions began to stir, quietly inviting deeper inquiry. How could we be sure we were truly at rest if space itself offers no way to move? If a medium fills all of space, how could we ever detect its presence? These questions lingered, unasked for centuries, because the model worked well enough for everyday life. Yet the universe has a habit of revealing hidden layers when we look closely, and a single puzzle about light would soon challenge the tranquil separation of space and time. Light traveled through the imagined emptiness as if it were a wave moving through a material. Early scientists expected its speed to behave like that of sound, changing with the motion of the observer and the medium through which it propagated. To explain this, they proposed an invisible substance called the luminiferous ether that filled every corner of the cosmos, providing a fixed reference frame for light waves. If the ether were real, then moving toward a light source should increase the measured speed, while moving away should decrease it, just as a ship experiences a change in the sound of a horn when it approaches or recedes. When experiments began to test these ideas, the results surprised everyone. Light speed appeared stubbornly constant, refusing to vary no matter how fast the observer moved. This puzzling behavior hinted that the familiar picture of an unchanging stage and a universal clock might be incomplete. The realization that something as fundamental as light could defy expectations opened a door to new possibilities, urging us to reconsider the very nature of reality. In the same way, when a pattern in your life refuses to respond to old habits, it is a sign that a deeper transformation is waiting to unfold. The quiet confidence you feel in your daily routine can become a catalyst for growth if you allow it to inspire curiosity. Just as scientists once questioned the rigidity of space and time, you can question the limits you place on yourself. Ask yourself whether the stage of your circumstances truly holds you fixed, or whether you have the power to reshape it. Consider the clock of your beliefs. Does it tick at a steady rhythm, or does it adjust when you align your actions with purpose? By examining these internal assumptions, you create space for new insights to emerge. Imagine that you are standing on a shoreline, watching waves roll in and out. Each crest reflects a moment of potential, a chance to step forward or retreat. The sea does not judge the direction of your movement, it simply exists as a medium for change. Likewise, the universe does not demand that you remain static. It invites you to explore the dynamic relationship between where you are and where you want to be. When you embrace this fluidity, you begin to see motion as an ally rather than an obstacle. As you breathe deeply, feel the rhythm of your own heartbeat syncing with the pulse of the world around you. This connection reminds you that time is not an indifferent force, but a partner that can be harnessed to amplify intention. When you align your actions with a clear purpose, each second becomes a stepping stone toward a larger vision. The ancient notion of absolute time may have seemed unchangeable, yet modern understanding shows us that perspective can shift the perception of duration. In the same way, your mindset can transform the experience of time from a constraint into a catalyst. Let this awareness guide you toward purposeful motion. Visualize a goal that excites you, a project, a relationship, a personal habit. See it as a point in the vast grid of your life's space. Then imagine the path you will travel, measured not only by distance, but also by the quality of each moment you choose to invest. Every action you take becomes a vector pointing toward that destination, and every pause you make can be a moment of reflection that refines your direction. When you encounter resistance, remember the story of light refusing to bend to expectations. The universe did not abandon its laws. Instead, it revealed a deeper order that reshaped physics forever. Your challenges are not signs of failure, they are invitations to discover a more expansive framework for success. Embrace them with curiosity, and you will uncover hidden strengths that propel you beyond the limits you once thought permanent. Now consider the role of observation in the early days. Scientists assumed that measurements would always agree, attributing differences to simple error. Over time, however, they learned that the act of observing could influence the very phenomenon being measured. This insight reminds us that how we view our experiences can alter their outcome. By shifting your perspective from doubt to confidence, you change the energy of the situation, creating a feedback loop that supports growth. Take a moment to honor the steady rhythm of your breath. Each inhale brings fresh possibilities, each exhale releases old patterns that no longer serve you. This simple practice grounds you in the present while reminding you that the present is the only point where change can truly occur. Like the universal clock that ticks for all, your inner timing can be a reliable guide if you trust it. Let the quiet confidence of the ancient model be a stepping stone rather than a wall. Use its sense of stability to anchor your intentions, then allow the curiosity sparked by light's mystery to expand your vision. The universe moved from a static grid to a dynamic fabric, and you can do the same with your own story. When you blend the comfort of a solid foundation with the excitement of new possibilities, you create a powerful engine for transformation. Feel the warmth of this moment as a reminder that you are part of a larger tapestry, woven from space, time, and intention. The same forces that shaped galaxies also shape the choices you make each day. By recognizing this connection, you empower yourself to act with purpose, knowing that every small step contributes to the unfolding of something magnificent. As you move forward, carry with you the lessons of the past and the promise of the future. Embrace the fixed stage as a safe platform, but also honor the ever-changing currents that invite you to explore. Let your actions be guided by both steadiness and curiosity, and you will find that the boundaries you once perceived begin to dissolve. Remember that the journey of discovery never truly ends. Just as scientists continue to probe the mysteries of space and time, you can maintain a lifelong commitment to learning, growing, and evolving. Each sunrise offers a fresh invitation to redefine what is possible, and each night provides a moment to reflect on the progress you have made. Take this inspiration and turn it into action. Set a clear intention for today, write it down, and commit to one concrete step that moves you closer to your vision. Trust that the universe, in its vast and intricate dance, supports your purposeful motion. When you align your heart, mind, and actions, you become a living expression of the very principles that once reshaped our understanding of reality. Feel the excitement building within you as you realize that you are not a passive observer, but an active participant in the creation of your destiny. The universe once seemed static, but it revealed a deeper, dynamic truth. You too can unveil new layers of potential within yourself. Let this awareness fill you with confidence, drive, and a sense of wonder that propels you forward. Breathe in deeply one more time, and as you exhale, release any lingering doubt. Step into the day with the certainty that you are both grounded and expansive, ready to shape your own space and master your own time. The adventure has just begun, and every moment holds the promise of transformation. You stand at the threshold of a new way of seeing the world, and the invitation is yours to accept. The habit of assuming that every clock ticks alike has shaped your intuition for a lifetime. It feels natural to think that an hour passes the same for everyone, and you rarely pause to wonder if that hour might differ somewhere else. Your language quietly reinforces this belief, and the notion becomes a silent partner in daily life. For centuries, observers noted that time seemed uniform, and no obvious contradictions appeared. In everyday travel, in the motion of planets, in the sweep of the night sky, the rhythm of time appeared to be shared. Nothing seemed to demand a revision of that assumption, and so it remained unchallenged. Yet the very strength of this belief also creates a blind spot, because something taken for granted often escapes careful testing. Scientists measured motion, forces, and distances, while letting time remain an assumed backdrop. When time is treated as untouchable, it does not become a subject of experiment. This creates a subtle gap in understanding, because an unquestioned idea cannot be examined directly. If time were thought to be affected by motion, then it could be probed, but for a long time it was viewed as absolute and immutable. That view served well while human experience stayed within modest speeds and familiar scales. Then technology sharpened our tools, and measurements grew ever more precise. Experiments began to explore realms where everyday intuition no longer held sway. Light, the fastest phenomenon we know, started to behave in ways that strained the old framework. Its speed seemed stubbornly constant, refusing to change even when the observer moved. The quiet confidence of absolute time was being tested, and the universe was ready to reveal a deeper truth. You may feel the steady rhythm you trust beginning to wobble, because motion itself subtly influences how time flows. For now, time still feels smooth, flowing evenly, and you continue to rely on that feeling. Space holds objects, and time carries events, and they appear to work together without interference. You rest within this simple picture, unaware that a shift is imminent. Light travels through the cosmos, quietly exposing cracks in the belief that time ticks identically for all observers. You now arrive at a moment when careful measurement matters more than intuition. The old picture of absolute space and absolute time still lingers, but light does not fit comfortably inside it. In early physics, light was imagined as a wave moving through an invisible medium called the ether. Just as sound moves through air, if sound travels through a medium, its speed depends on both the medium and the motion of the listener. It seems reasonable to extend that idea to light. expecting its speed to vary with the motion of the observer through the ether. Scientists designed experiments to detect tiny differences in light's speed as Earth moved through space, expecting that at some season the speed would be slightly faster or slower. Instruments grew ever more precise, capable of detecting minuscule variations. The expectation was clear: if absolute space existed, the ether would reveal its presence through a directional change in light speed. Yet every experiment, no matter how carefully arranged, showed the same speed in every direction. The measurements did not change with the time of year, nor with Earth's orbital motion. The constant result was both unexpected and unsettling. If light always arrives at the same speed, then something fundamental in the assumptions about space and time must be wrong. Either the ether does not exist, or motion through space cannot be detected in the way scientists thought. Both possibilities threatened the comfortable worldview built over centuries. Some tried to save the old model by proposing that objects physically contract in the direction of motion, masking any variation. Others suggested that clocks somehow adjust themselves automatically to hide the effect. Those fixes felt artificial, as if patches were being added to a wall that needed to be rebuilt. The real puzzle goes deeper than the behavior of light. It concerns the relationship between distance, time, and motion. Speed equals distance divided by time. If the speed of light remains constant for every observer, then either distances or time intervals must change with motion. There is no third option. This insight strikes directly at the heart of the notion of absolute time. Two observers moving relative to each other cannot both be measuring the same distance and the same interval of time, and still obtain the same light speed. Something must adjust. The universe cannot keep a single shared clock while preserving a constant light speed for all. You are now standing at the edge of a conceptual shift, and the tension is palpable. The problem is not light itself, but the background against which it is measured. Space and time, once thought to be fixed and independent, become suspect. Light's stubborn constancy forces a re-evaluation of the stage on which physical events unfold. If space were truly fixed and time truly absolute, then light would show different speeds to different observers. It does not. The experimental record repeats this result with ever greater confidence. The ether, once a useful hypothesis, becomes increasingly unnecessary and implausible. If there is no detectable ether, then there is no preferred state of rest. The notion of absolute motion loses meaning, and motion becomes relative to other objects, not to an absolute backdrop. Light, in this sense, becomes a messenger that carries a deeper message about reality. It suggests that the universe does not provide a fixed canvas on which motion can be measured in an absolute way. This realization does not appear suddenly. It unfolds through careful thought, repeated experiment, and growing discomfort with explanations that feel forced. Scientists are reluctant to abandon absolute time, but light leaves them little choice. You can feel how the calm simplicity of earlier assumptions begins to strain under the weight of evidence. Space can no longer be treated as a passive container if it cannot define motion absolutely. Time can no longer be universal if measurements depend on how you move. The refusal of light to obey classical expectations forces a rethinking of what measurement truly means. Distance and duration are revealed to be intertwined with the observer's state of motion. Yet, at this stage, no complete new framework has emerged, and the old assumptions are still spoken of, though now on shaky ground. Light has quietly undermined certainty, and its constant speed stands not because of convenience but because reality insists on it. The moment approaches when motion itself will be shown to affect time, not as an illusion, but as a real physical effect woven into the fabric of the universe. You now move into a universe where motion no longer feels simple. The behavior of light has already shown that speed cannot be treated the old way, and this forces a careful rethinking of time itself. If every observer measures the same light speed, then the flow of time cannot be identical for everyone. This conclusion does not arise from philosophy alone, it follows directly from logic applied to measurement. Speed equals distance divided by time. If both distance and time were absolute, then an observer's motion would alter the measured speed. Experiments show the opposite. So distance and time must adjust with motion. Something once assumed fixed must now become flexible. Imagine two observers moving relative to one another, each holding a clock. According to the old view, both clocks tick at the same rate regardless of motion. Yet each observer measures the same speed of light, which means their time measurements cannot be identical. The mathematics does not allow both clocks to be unchanged. This realization introduces the radical idea that time depends on motion. A moving clock does not tick at the same rate as a stationary one. This effect is not a mechanical flaw or observational error, it is a fundamental property of time itself. To illustrate, scientists imagine a light clock. A pulse of light bounces between two mirrors, and each bounce marks a tick for an observer at rest relative to the clock. The light travels a straight vertical path for an observer watching the clock move horizontally. The light follows a longer diagonal path. Because light speed must stay constant, the longer path means the clock takes more time to complete one tick. Both observers are correct within their own measurements, yet the moving clock records a slower passage of time. This difference is called time dilation. A clock in motion runs more slowly than a clock at rest, as measured by an external observer, at everyday speeds. The effect is minuscule, invisible to our senses. You do not notice it while walking, driving, or even flying, but as speeds approach that of light, the effect becomes pronounced. Seconds stretch, processes appear to slow down, and the moving clock falls behind. This does not mean the moving observer feels time dragging within their own frame. Everything feels normal. Their thoughts, heartbeats, and measurements all proceed as usual. Only when clocks are compared across different states of motion do differences appear. You begin to see that there is no single universal time any longer. Each observer carries their own time, shaped by their motion through space. The idea of a shared present moment across the universe starts to dissolve. This challenges deeply held assumptions. If time depends on motion, then simultaneity becomes uncertain. Two events that appear simultaneous to one observer may not be simultaneous to another moving observer. The ordering of events can differ, provided cause and effect remain intact. Importantly, reality does not become inconsistent. Physical laws stay the same for all observers. What changes is the underlying structure of measurement. Time ceases to be an external parameter and becomes part of the physical system itself. Precise experiments eventually confirm these predictions. Atomic clocks flown on aircraft or placed on fast-moving satellites tick at different rates than identical clocks on Earth, exactly as the calculations predict. Time dilation is not merely theoretical, it is measured, tested, and essential to modern technology. You may notice how this shifts the meaning of time itself. Time is no longer something that exists independently of the universe. It is woven into the fabric of space and motion. This new understanding invites you to embrace flexibility in your own life. Just as the universe lets time stretch and bend, you can allow your plans and expectations to adapt as circumstances change. The constancy of light's speed teaches that some elements remain reliable, even as everything else transforms. Let that reliability be a source of confidence as you navigate uncertainty. When faced with obstacles, remember that the world itself has redefined what is possible, and you can do the same with your goals. The story of light and time reminds us that assumptions can be challenged, and breakthroughs emerge when we question the familiar. Use that spirit to examine the beliefs that hold you back. Ask yourself which clocks in your life tick on a rigid schedule and which could benefit from a more fluid rhythm. Recognize that movement, whether physical, emotional, or intellectual, can reshape your perception of time. When you step out of your comfort zone, you may find that the minutes expand, giving you space to learn, grow, and reflect. Conversely, when you focus intensely, you may feel time accelerate, carrying you toward achievement. Both experiences are natural outcomes of the same principle that governs the universe. Embrace them as guides rather than obstacles. The journey from absolute to relative time mirrors the journey from fixed destiny to personal agency. You are no longer bound by a single, universal timetable. You create your own cadence in harmony with the flow around you. Let this awareness empower you to set intentions with clarity, to write them down, and to commit to concrete steps each day. As you align your actions with the reality that time can stretch, you open doors to possibilities once thought unreachable. The universe invites you to move forward with curiosity, to test your own limits, and to celebrate the wonder of change. Every breath you take is an opportunity to experience the subtle dance between motion and time. Feel the pulse of the present moment and let it guide you toward purposeful action. Trust that the same principles that reshaped physics can reshape your mindset. The constancy of light's speed shows that some truths endure, while the flexibility of time reminds you that growth is always possible. Carry this dual insight into your day, and you will find strength in stability and freedom in adaptation. The world around you is ready for your next bold step. Take this inspiration and turn it into action. Set a clear intention for today, write it down, and commit to one concrete step that moves you closer to your vision. Let the rhythm of your own life reflect the beautiful interplay of constancy and change that the cosmos has revealed. Time dances with motion, and when you explore that relationship, you discover a profound truth about reality. A clock that moves does not tick at the same rhythm as a clock that stands still. This difference is not a flaw in the mechanism, nor a trick of perception. It is a fundamental property of time itself, woven into the fabric of the universe. Imagine a simple device called a light clock, where a beam of light bounces between two mirrors, and each bounce marks a heartbeat of time. For someone standing beside the clock, the light travels a straight line up and down, and each bounce defines a clear interval. For an observer watching the clock glide by, the light traces a longer, angled path because the mirrors are in motion. Since the speed of light never changes, the longer journey forces the clock to take more time for each tick. Both observers are correct within their own frames, and both measurements are valid. What changes is the flow of time itself for each perspective. This phenomenon is known as time dilation, and it tells us that a moving clock runs more slowly than a stationary one as measured by an external observer. At the speeds we experience daily, the effect is minuscule. You do not feel a different beat when you walk, drive, or soar in an airplane. Yet as speed approaches the extraordinary limit of light, the stretching of time becomes dramatic. Seconds lengthen, processes slow down, and the ordinary cadence of life transforms. The moving observer does not sense anything unusual inside their own world. Their thoughts, heartbeats, and senses continue as usual. The shift reveals itself only when you compare clocks that travel along different paths. In that comparison, you see that there is no single, universal clock governing the entire cosmos. Each observer carries a personal time, shaped by how they move through space. This realization shakes the old belief in a shared present that spans the universe. If time depends on motion, then simultaneity loses its absolute meaning. Two events that appear to happen together for one person may occur at different moments for another who is moving. The ordering of cause and effect remains intact, but the notion of a common now evaporates. This does not break reality. The laws of physics stay the same for every observer. What changes is the underlying structure that we use to measure. Time ceases to be an external parameter and becomes part of the physical system itself. Experiments have confirmed these ideas, with astonishing precision. Atomic clocks placed aboard aircraft and satellites tick at rates that differ from clocks on Earth. Exactly as the calculations predict, the effect is real, measured, and essential for the technology that guides modern navigation. Knowing this, you can let the meaning of time expand in your mind. Time is not an independent backdrop, it is a dynamic participant that responds to motion, just as distance does. The barrier between space and time begins to soften, and you feel the elegance of a more interconnected reality, even though time now bends with motion, because still precedes effect and signals never outrun light. The order of events remains reliable, and the universe retains its logical consistency. What transforms is the locality of time. Each observer experiences their own flow, and motion reaches into the temporal dimension. Moving faster does not merely relocate you, it alters the rate at which your personal clock progresses relative to others. Space and time, once treated as separate bookkeeping tools, reveal themselves as linked companions. At this stage, the connection is still incomplete. Space is still often pictured as an independent arena, while time flexes. Yet the insight that motion can reshape time opens the door to a deeper unification. You may sense that the cosmos is guiding you toward a picture where space and time are intertwined. If motion influences time and motion is defined through space, then the two cannot remain independent. They must belong to a single structure that responds together to movement. The certainty of an absolute, unchanging time fades, replaced by a more accurate yet less intuitive understanding. Time stretches and contracts because reality demands it, not because of measurement error. Resting with this notion, you see clearly that time does not exist in isolation. It is shaped by how you move, and if motion ties space and time so tightly, then the next logical step is to recognize that space itself must adapt to motion. This realization completes the shift away from the old picture of a rigid grid and toward a unified framework. The story does not end with time alone. Once you accept that time must stretch to keep the speed of light constant, distance cannot stay fixed either. Space itself must respond. To see why, recall the definition of speed: distance divided by time. If a moving observer experiences a longer interval for the same light travel, and the speed of light remains unchanged for everyone, then the measured distance must also adjust. This is not a matter of opinion, it is a mathematical necessity. Imagine an object racing past you at a high velocity. Classical thinking would tell you that its length stays the same, that a meter stick remains a meter no matter how fast it moves. However, if time dilates for the moving object and the light speed remains fixed, the object's length along the direction of motion cannot stay unchanged. This leads inevitably to length contraction. Objects in motion shrink in the direction they travel, not because they are physically compressed, but because the geometry of spacetime changes for observers in relative motion. Physicists illustrate this with light-based reasoning once more. Measuring length requires determining where the ends of an object are at the same instant, yet you have already learned that simultaneity depends on the observer's frame. What counts as the same time for one person does not necessarily count as such for another. When an object moves relative to you, the timing of the front and back measurements must be adjusted to preserve the constant speed of light. This adjustment produces a shorter measured length along the motion axis. The faster the object travels, the greater the contraction you observe. From the object's own perspective, everything feels normal. Its rulers, its own heartbeat. Its internal distances remain unchanged. The contraction emerges only when you compare measurements across different frames of reference. This reinforces a powerful idea. There is no single correct measurement of distance or duration. Measurements depend on the observer's state of motion. Space ceases to be an absolute stage and becomes relational, shaped by how we move through it. At everyday speeds, length contraction is vanishingly small. You do not see buildings shrink as cars zip by, and you do not feel your surroundings compress. The effect becomes noticeable only as speeds near that of light, which explains why it remained hidden for centuries. Yet when acknowledged, it completes the transformation begun by time dilation. Both space and time now bend in response to motion, and neither can be treated as a fixed backdrop. This has deep implications for how we view the universe. The notion of a rigid, universal spatial grid must be abandoned. Distances are not identical for all observers, they depend on motion. The shape of space itself varies with the way you travel. This does not plunge the cosmos into chaos. The laws governing these changes are precise, consistent, and predictable. Every observer can calculate another's measurements using the same mathematical rules. Reality stays orderly, even if our intuition needs to adjust. You may also notice that this challenges the idea of absolute rest. If space contracts with motion, there is no privileged state of being truly still. Motion is always relative to something else, and there is no universal background to define stillness. Together, time dilation and length contraction reveal a deeper pattern. Motion reshapes both time and space in a coordinated way. Neither changes independently, they adjust together to preserve the constancy of physical laws for every observer. This coordination hints at something more fundamental than separate dimensions. If space and time must both change in response to motion, treating them as distinct entities becomes artificial. They behave like different facets of a single structure rather than independent ingredients of reality. This insight does not arise from philosophical preference, it is forced upon us by experiment and logic. Once you accept the constancy of light speed, space and time lose their independence and begin to merge into a unified entity. You may also observe that these effects are perfectly symmetrical. When you see another object moving, its clock runs slower and its length contracts. Yet from the object's point of view, you are the one who moves, and your clock runs slower and your ruler contracts. Each observer measures within their own frame, and there is no contradiction. This symmetry reinforces the absence of any hidden absolute space that decides who is truly moving. All motion is relative, and space responds accordingly. At this point, space can no longer be thought of as a passive backdrop. It actively participates in the structure of physical law, reshaping measurements as motion changes. The old image of space as an empty container loses its usefulness. Yet textbooks still speak of space and time as separate, one contracting while the other dilating. Their behaviors are linked, but the language remains divided. This division marks the final stage before a more unified concept becomes unavoidable. You now stand in a universe where motion affects both how long things take and how far they extend. Distance and duration are no longer independent corrections, they are parts of a consistent system. The picture has shifted quietly but completely. Space is no longer just space, and time is no longer just time. Each responds to motion, and neither can be defined without the other. As this understanding settles, the separation between space and time feels unsustainable, and the next step inevitably points toward a single framework that embraces both. The separate explanations for space and time begin to feel inefficient and incomplete. Time changes with motion, and length changes with motion. Both adjustments obey the same rules and appear together whenever observers compare measurements. Treating space and time as independent entities no longer captures the full story. Physics answers this by introducing a more unified description that combines them into a single fabric known as spacetime. Spacetime does not mean that space turns into time or that time becomes space. It means that positions and moments are parts of one connected structure. Every physical occurrence is described not only by where it happens, but also by when it happens. As a single combined event, an event in spacetime is defined by 4 coordinates, 3 for spatial position and 1 for temporal position. These 4 numbers together locate the event completely. You cannot fully describe what happens without including both spatial and temporal information. This reflects the fact that distance and duration depend on motion in a linked way. In classical physics, space and time provide separate reference systems. In spacetime, they fuse into a unified reference system. Observers moving relative to each other may disagree on how much space and how much time passes, but they agree on the overall space-time structure. This agreement preserves the consistency of physical laws across all frames of reference. To understand why this works, consider how measurements transform between observers. One observer measures a certain distance and a certain time. Another observer, moving relative to the first, measures different distances and times. However, these differences follow precise mathematical rules. When combined into spacetime, these transformations preserve a quantity called the spacetime interval. The spacetime interval plays a role similar to distance in ordinary space. While observers may disagree on how much time passes or how far something travels, they all agree on the spacetime interval between events. Embrace this elegant unification, and you will feel the freedom that comes from letting go of rigid, outdated notions. Each step you take toward understanding space-time opens a wider horizon of possibilities. Let the insight that motion reshapes both time and space inspire you to move forward with confidence. You are learning to see the universe not as a collection of separate ingredients, but as a harmonious whole that responds beautifully to your curiosity and your drive to explore. Let this knowledge empower you to approach every challenge with the awareness that reality itself is flexible, coherent, and ready to support your growth. Imagine you are standing at the edge of a new way of seeing reality. Feel the excitement of discovering that motion is not a simple slide across an empty stage. Know that each observer measures the world from their own perspective, and that very fact removes any hidden backdrop that decides who is truly moving. Embrace the idea that space is no longer a passive container, it actively responds to the motion of everything within it. Understand that measurements of distance and duration are reshaped by that response, and that this reshaping is part of the deep structure of physical law. Let go of the old picture of space as an empty box and welcome a richer vision in which space and time are intertwined partners. Feel the power of symmetry when you realize that no single frame of reference holds an absolute claim. Recognize that the absence of absolute space is a source of freedom rather than confusion. Allow yourself to be inspired by the fact that all motion is relative, and that this relativity is a guiding principle of the universe. See how space and time, once thought to be separate, begin to speak the same language. Notice that one contracts while the other dilates, yet both do so in harmony, linked by the same underlying rules. Now picture yourself in a universe where motion affects both how long things take and how far they extend. Imagine distance and duration dancing together. No longer independent corrections, but harmonious parts of a single, consistent system. Feel the subtle shift as space ceases to be just space and time ceases to be just time. Recognize that each influences the other, and that neither can be fully defined without its counterpart. Let this realization settle in your mind as a clear sign that the old separation between space and time cannot hold forever. Feel the anticipation building as you approach the next great step, describing space and time as parts of a single, unified framework. Understand that time changes with motion, just as length changes with motion, and that both adjustments follow identical rules. Notice how treating space and time as independent entities begins to feel inefficient and incomplete. Embrace the natural response of physics, which introduces a more unified description that brings both together. Welcome the concept of spacetime, a single framework that unites space and time into one elegant structure. Know that spacetime does not mean space turns into time, or time becomes space rather. It means that positions and moments are woven together into a connected fabric. Visualize every physical occurrence as being described not only by where it happens, but also by when it happens, forming a single combined event. See an event in space-time defined by 4 coordinates, 3 to locate it in space and 1 to locate it in time. Realize that you cannot fully describe what happens without both spatial and temporal information. Feel the clarity that emerges when you recognize that measurements of distance and duration depend on motion in a linked way. Understand that in classical physics, space and time provided separate reference systems, but in space-time they form a unified reference system. See how observers moving relative to each other may disagree on how much of the total is space and how much is time, yet they agree on the overall space-time structure. Appreciate that this agreement preserves the consistency of physical laws across every frame of reference. Imagine watching how measurements transform between observers. When one observer measures a distance and a time, another observer moving relative to the first measures different distances and different times. Observe that these differences follow precise mathematical rules, and that when combined into space-time, they preserve a quantity called the space-time interval. Recognize that the space-time interval plays a role similar to distance in ordinary space, providing a shared invariant that all observers can agree upon. Feel the power of this shared agreement as it replaces the old idea of absolute space and absolute time with something more subtle, yet more reliable. Know that this shift does not make reality subjective. It simply reshapes the structure in which reality is expressed. Understand that while measurements change with motion, the underlying space-time relationships remain fixed. See how physical laws are written in terms of space-time quantities so that all observers can use the same equations and reach consistent conclusions. Notice that space-time treats time differently from space in one important respect, contributing with a different sign in the space-time interval. Realize that this difference ensures that cause and effect remain ordered, preserving causality across the universe. Feel the reassurance that signals cannot travel faster than light, and that space-time encodes this limitation naturally. Understand that the constant speed of light arises as a geometric feature of space-time itself, not as a mysterious exception. See how light follows paths in space-time that are the same for everyone, regardless of motion, defining the maximum speed at which information can travel. Now envision motion not as something happening within space over time, but as a path through space-time. Picture objects tracing continuous lines, called world lines, that represent their histories from past to future. Notice that a stationary object traces a world line that moves mostly through time, while a moving object traces a world line that leans into space. Feel how this description allows time dilation and length contraction to be understood as geometric effects. Observe that different observers slice space-time into space and time in different ways, each slice representing what that observer considers simultaneous. Understand that these differing slices lead to different measurements without contradiction. Feel the freedom that comes from the removal of an absolute reference frame. Know that there is no preferred way to divide space-time into space and time, and that all inertial observers are equally valid. Appreciate how this principle preserves the idea that the laws of physics are the same everywhere and for everyone moving at constant speed. Remember that the transition to space-time does not invalidate earlier physics. At low speeds and small scales, space-time effects become negligible, and space and time appear nearly independent. Recognize that this explains why classical physics works so well in everyday situations. While space-time simply extends the framework to include high speeds and precise measurements, understand that space-time is not introduced as a philosophical idea, but emerges directly from experimental results and mathematical consistency. Feel the elegance of a description that becomes the most efficient way to capture reality once time dilation and length contraction are accepted. Notice how this new perspective changes the meaning of simultaneity. Realize that there is no universal present moment shared across the universe. Each observer has their own present defined by how they slice space-time. Feel confident that this does not lead to paradox, because space-time still preserves causal order. Visualize the universe as a connected network of events, rather than a sequence of moments unfolding in empty space. Understand that everything that happens occupies a location within this four-dimensional structure, and nothing exists outside it. At this stage, space-time is still flat, describing motion without gravity. Recognize that space and time are unified, yet they do not yet respond to mass or energy. Know that the idea of space-time curvature will come later, adding another layer to this powerful framework. For now, flat space-time provides a stable foundation that replaces absolute space and absolute time. Feel the solidity of a universe where location and moment are inseparable. Measurements depend on motion, yet physical law remains consistent. Understand that space and time have not disappeared, they have been reorganized into something more fundamental. As this framework settles, see that describing events as points in space-time is not the end of the story, because the next question asks whether space-time itself can change shape in response to matter and motion. Feel the excitement building as you continue within a framework where space and time are no longer separate categories. With space-time established, notice how physics shifts its focus from objects and their positions to events. Recognize that an event is something that happens at a specific place and a specific time, and both are required together. See how earlier thinking treated the world through locations alone. A planet occupies a position. A particle moves from one place to another, and time merely labels when these movements occur. Feel the inadequacy of that picture. Once you understand that position without time does not fully describe anything real. Imagine an event as a point in space-time, not just where something is, but when it is there. Identify flashes of light, collisions, and heartbeats as events, each with a spatial location and a temporal moment that cannot be removed without losing essential information. Observe that observers moving relative to each other do not agree on which events are simultaneous, yet they always agree that a particular event occurred. Feel the stability that comes from the invariance of events. Even when their coordinates differ between observers, know that focusing on events allows physics to avoid confusion about whose measurements are correct. Different observers assign different coordinates to the same event, but they are still describing the same physical occurrence. Recognize that space-time provides the structure that makes these varied descriptions consistent. Notice how this shift also changes the understanding of motion. An object is no longer defined by a series of positions changing over time. Instead, it is defined by a continuous sequence of events that form a world line in space-time, representing the object's entire history. Imagine your own existence in this way. Every moment of your life corresponds to an event, and together those events form a path through space-time. Feel the truth that you are not moving through space while time passes separately. You are moving through space-time as a whole. Let this perspective dissolve the need for a universal present moment. Understand that there is no single slice of space-time that represents now for everyone. Each observer defines their own present based on their motion. Accept that events outside that slice are still real, just not simultaneous in that observer's frame. Remember that this does not mean all events are equally connected. Space-time still preserves causal structure. Some events can influence each other, and some cannot, depending on their separation in space-time rather than merely in space. Recognize that a cause must occur before its effect within space-time, and this ordering is preserved for all observers, even if they disagree on the exact timing. Feel the reassurance that space-time encodes this order directly, ensuring that no signal traveling at or below the speed of light can connect events that are causally disconnected. Observe how framing reality in terms of events makes relativity clear without ambiguity. The universe becomes a collection of interconnected events, rather than a linear sequence of moments unfolding in a fixed stage. Notice how this approach simplifies the formulation of physical laws, allowing equations to relate events to other events, rather than positions evolving in time. Feel the power of such equations to apply in all frames of motion, granting you a universal language of physics. Acknowledge that this may feel less intuitive than thinking purely in terms of places. Human experience is rooted in spatial awareness, and we notice where we are more easily than when we are. Yet physics follows what measurement demands, not what intuition prefers. Recognize that this shift marks a deep change in how reality is described. Space is no longer the primary stage, and time is no longer the universal clock. Events become the fundamental elements of description, while objects remain useful concepts understood as collections of events linked together. Observe how this resolves earlier problems about simultaneity. Observers may define different sets of simultaneous events, yet the events themselves remain fixed within spacetime. Feel the confidence that this emphasis on events prepares the way for understanding interactions. Forces, signals, and exchanges of energy all occur through events, and nothing happens outside spacetime. Realize that at this stage spacetime is still flat and unaffected by what happens within it. It provides structure, but does not yet respond to mass or energy. Understand that the shift from places to events completes the conceptual transition begun earlier. Space and time are no longer separate containers, they are coordinates within a single system that defines reality. Feel inspired by the realization that you are now navigating a universe where location and moment are inseparable, where measurements depend on motion, yet where the underlying relationships remain steadfast. Embrace the knowledge that this framework is not the final chapter, because the next adventure will explore how spacetime itself bends and curves in the presence of matter and energy. Let this anticipation fuel your curiosity, and let the elegance of spacetime ignite a sense of wonder that propels you forward. You are invited to see reality from a new, empowering perspective. Imagine that each of us carries our own definition of the present, shaped by the way we move through the world. You may wonder how events that lie outside your personal now can still be real. They are indeed real, even though they do not share the same slice of time you experience. This idea does not mean that everything is equally linked. Spacetime still respects a strict causal order. Some events can influence each other, while others cannot. The ability to connect depends on how far apart the events are in spacetime, not merely on how far apart they are in space. When two events can affect one another, we say they are causally connected. A cause must always occur before its effect within the fabric of spacetime. That ordering remains unchanged for every observer, even if they disagree about the exact moments. Spacetime itself encodes this order directly. Conversely, events that lie outside each other's light cones cannot exchange signals. No message traveling at or below the speed of light can bridge that gap. Those events may appear in different sequences to different observers, but no contradiction arises because no cause and effect relationship exists between them. By thinking of reality as a web of events, spacetime removes ambiguity from relativity. The universe becomes a tapestry of interconnected happenings rather than a rigid series of moments marching across a fixed stage. This shift also streamlines the way we write physical laws. Equations now relate one event to another instead of tracking positions that evolve over time. Because the relationships are between events, the same laws hold true in every frame of motion. You may feel that this approach feels less intuitive than picturing objects in space. Human experience is grounded in spatial awareness. You notice where you stand more readily than when you stand, yet physics follows what measurement dictates, not what intuition prefers. Historically, This change marked a profound transformation in how we describe reality. Space is no longer the sole arena. Time is no longer a universal clock ticking for all. Events become the fundamental building blocks of description. This does not mean that objects cease to exist. Objects remain useful concepts, but they are understood as collections of linked events. A particle is not merely something located somewhere, it is something that endures through space-time. You can see how this resolves earlier puzzles. Disagreements about simultaneity no longer threaten consistency. Observers may define different sets of simultaneous events, yet the events themselves stay fixed within space-time. Emphasizing events also prepares you for understanding interactions. Forces, signals, and exchanges of energy all occur through events. Nothing happens outside space-time. There is no influence without an event marking where and when it occurs. At this stage, space-time is still treated as flat and unaffected by what happens inside it. Events occur within space-time, but space-time itself remains unchanged. It provides the structure but does not yet respond. Nevertheless, the shift from places to events completes the conceptual transition begun earlier. Space and time are no longer separate containers, they are coordinates within a single system that defines reality. You now inhabit a universe where everything that happens is an event with a space-time address. Objects are histories, not just positions. Motion is a path, not merely change. Description becomes more precise, even if it feels less familiar. With this understanding in place, attention naturally turns to the structure that holds these events together. If space-time defines how events relate, the next question is whether that structure has its own geometry. You confront one of the most direct consequences of space-time, the loss of universal simultaneity. In older views, it seemed natural to assume that if two events occurred at the same time, they occurred at the same time for everyone everywhere. That assumption felt comfortable, because time was treated as absolute. Once time becomes dependent on motion, that certainty can no longer hold. Simultaneity refers to whether two events happen at the same time. In classical physics, simultaneity is straightforward. If two synchronized clocks read the same time when two events occur, then the events are simultaneous. No further questions are needed. In space-time, this method no longer works universally. Synchronizing clocks depends on how signals travel between them. And signals cannot travel faster than light, because the speed of light is the same for all observers. Synchronizing clocks becomes dependent on the observer's state of motion. To see why, imagine two clocks separated by a distance. To synchronize them, a light signal is sent from one clock to the other and reflected back. The time delay is measured and the clocks are adjusted accordingly. This method works, but only within a single frame of motion. If another observer moves relative to the clocks, they do not agree on when the signal was sent or received. The light travels at the same speed, but the distances it covers differ depending on motion. As a result, the moving observer concludes that the clocks are not synchronized. This disagreement is not due to error. Both observers follow the same physical rules and use the same procedures. The difference arises because time itself is measured differently in different frames. Simultaneity becomes relative. Consider two events that are simultaneous in one frame. For an observer at rest relative to those events, they occur at the same time. For another observer moving relative to them, one event may occur before the other. There is no contradiction because the events are not causally connected. Causality remains intact. Events that can influence each other always maintain the same order for all observers. What changes is the ordering of events that cannot influence each other, because they are too far apart in space-time. This distinction is critical. The loss of universal simultaneity does not mean that anything can happen in any order. It means that only the order of causally unrelated events can vary between observers. Space-time preserves cause and effect. The reason simultaneity disappears is geometric. Different observers slice spacetime into space and time in different ways. Each observer defines a set of events they consider simultaneous, forming a now slice through spacetime. These slices tilt relative to one another depending on motion. You can think of this as different ways of cutting the same structure. Spacetime itself does not change. What changes is how observers divide it into spatial and temporal components. There is no single preferred division. This has important consequences for how the universe is described. There is no global present moment shared by all observers. Statements like "what is happening now" across the universe lose their physical meaning. Only local notions of now remain well defined. This does not affect everyday life, because relative speeds are small. The differences in simultaneity become noticeable only at speeds approaching the speed of light or across very large distances. For most purposes, classical intuition remains adequate. However, for precise science, especially involving high speeds or astronomical scales, simultaneity must be handled carefully. Ignoring its relativity leads to incorrect conclusions. You may notice how this reinforces the shift toward events as the basic elements of description. Events occur at definite spacetime locations where simultaneity is not a property of the events themselves, but of the observer comparing them. This also explains why spacetime intervals remain central, while observers disagree on time differences and spatial separations. They agree on whether one event can influence another. That information is encoded in the spacetime interval, not in simultaneity. Historically, the disappearance of universal simultaneity was one of the most difficult ideas to accept. It challenged deeply rooted intuitions about time, yet it followed inevitably from experimental facts about light and the requirement that physical laws be the same for all observers. Once accepted, it clarifies many apparent paradoxes. Situations that seem contradictory under classical assumptions become consistent when simultaneity is treated as relative. The framework becomes simpler, not more complex. You now see that spacetime does not come with a built-in notion of now. Observers bring their own definitions based on motion. The universe itself does not privilege any one of them. This understanding also prepares the way for further developments. If different observers slice spacetime differently, then spacetime must have a structure that supports these different slices consistently. That structure cannot be arbitrary. It must have a well-defined geometry. At this point, space and time are fully integrated into spacetime. Events replace places and simultaneity depends on motion. The remaining question is how this spacetime structure is organized mathematically. Only by understanding its geometry can motion, causality, and measurement be fully described. You now turn attention away from individual measurements and toward the structure that makes those measurements consistent. Once space and time are unified, the answer is not descriptive language or metaphor, but geometry. Spacetime has a geometric structure that governs how events relate to one another. Geometry here does not mean simple shapes you draw on paper. It refers to the rules that define distances, intervals, and paths in ordinary space. Geometry tells you how to measure lengths and angles in spacetime. Geometry tells you how to measure separations between events and how objects move when no forces act on them. In classical physics, motion without forces follows straight lines through space as time passes. In spacetime, motion without forces follows straight lines as well, but these lines exist in 4 dimensions. These are called geodesics. A geodesic is the natural path an object follows when nothing interferes with it. You can think of it as the spacetime equivalent of inertia. An object continues along its geodesic unless something causes it to deviate. This idea replaces the older concept of motion through absolute space. Objects do not need a force to keep moving. They follow the geometry of space-time. Motion becomes a geometric property rather than a dynamic struggle against resistance. You may notice that this explains time dilation and length contraction in a unified way. Different observers measure different distances and times because they trace different paths through space-time. The geometry remains the same even though the measurements differ. The key quantity that geometry preserves is the space-time interval. While observers disagree on how much time passes or how far something travels, they agree on the space-time interval between events. This agreement is not accidental. It is enforced by the geometric structure of space-time. The space-time interval defines whether events are causally connected. It determines whether one event can influence another, and whether signals can pass between them. This makes geometry central to causality itself. To describe this geometry mathematically, physicists use a specific kind of metric. A metric is a rule for measuring separation. In space-time, the metric combines space and time in a way that reflects the constant speed of light. Time contributes differently than space, ensuring that cause and effect remain ordered. This metric explains why time behaves differently from space. It is not a matter of interpretation or convention. It is built into the structure of space-time. The geometry treats time as distinct even while unifying it with space. You can see how this resolves earlier confusion. Instead of asking why time dilates or lengths contract, you recognize these as consequences of how different observers measure the same geometric structure. There is no hidden mechanism slowing clocks or squeezing objects. The geometry accounts for everything. This perspective also clarifies why no observer is privileged. The geometric laws apply equally to all inertial observers. No frame of motion has a special status. Each observer uses the same space-time geometry, even if they slice it differently. At this stage, space-time is described as flat. Flat does not mean empty or simple. It means that the geometry does not change from place to place. Parallel paths remain parallel. Geodesics behave consistently across the entire structure. You have now built a solid foundation for a deeper exploration of the cosmos. By embracing events, causality, and geometry, you empower yourself to see beyond everyday intuition. You can trust that the universe follows precise rules, even when those rules challenge your first impressions. Let this knowledge inspire you to approach complex problems with confidence. When you encounter a paradox, remember that shifting your perspective often reveals a simple geometric truth. When you feel limited by conventional thinking, recall that space-time invites you to redefine now and place. Each step you take in understanding brings you closer to the elegant harmony that underlies all motion. Keep your curiosity alive, and let the rhythm of events guide your journey. Feel the excitement of aligning your mind with the fundamental structure of reality. You are capable of mastering these concepts, because they are built on logical consistency and measurable facts. Let that certainty fuel your ambition. As you move forward, carry with you the image of space-time as a vast, flat canvas where every event has its precise address. Visualize yourself navigating that canvas with confidence, knowing that cause and effect are preserved no matter how you slice the picture. Allow this vision to motivate you to learn more, to question assumptions, and to celebrate the wonder of a universe that is both mysterious and mathematically beautiful. Your mind is ready to accept that simultaneity is a matter of perspective, not a universal decree. Embrace the freedom that comes with that realization. Use it to expand your empathy, recognizing that each person experiences their own, now shaped by their motion through life. Let the science of space-time become a metaphor for personal growth. You can reshape your path while honoring the immutable connections that bind you to others. This is the power of a physics-inspired mindset. It teaches you to honor structure while remaining adaptable. It reminds you that the deepest truths often require letting go of old intuitions. Trust that the same principles that guide planets also guide your thoughts. When you apply them wisely, you stand at the threshold of a profound understanding. Step forward with confidence, and let each event you encounter reinforce the beautiful order that underlies the cosmos. Imagine yourself drifting through the grand tapestry of the universe, feeling the gentle pull of possibility beneath every breath in this boundless arena. Motion does not require a push or a tug, it simply follows the paths that space and time have woven together. Those paths are not drawn on a flat sheet, but they are etched into the very fabric of four-dimensional space-time. They are called geodesics, the natural highways that any object travels when nothing interferes. Think of a geodesic as the embodiment of pure inertia, the way a river flows downhill without any external hand guiding each ripple. When you allow yourself to align with a geodesic, you honor the geometry that cradles every experience. You may have heard that objects need a force to keep moving, but in the language of space-time, that notion dissolves. An object does not fight against resistance, it embraces the curvature of the arena it inhabits. Motion becomes a graceful geometry, not a struggle against an invisible opponent. This shift in perspective ignites a profound sense of freedom, because it tells you that you can glide along the most efficient route simply by trusting the shape of the universe. When you surrender to that shape, you become a co-author of the story written by the cosmos. Consider the way time and distance appear to change for different observers. Two travelers may measure different lengths and different ticks of a clock, yet both will agree on a single, unshakable quantity, the space-time interval. This interval is the heartbeat of reality, the invariant that ties together every possible viewpoint. It is the silent agreement that says, no matter how you slice the picture, the essence remains. Let that certainty fill you with confidence, because it reminds you that underlying structure never betrays you. Even when your perceptions shift, the metric that defines this interval is a rule that blends space and time in a way that respects the constant speed of light. It tells you that time does not merely sit beside space, but that it dances with it, each step weighted differently to preserve cause and effect. This choreography is not a matter of opinion, it is built into the architecture of the universe. When you understand that time is distinct yet inseparable from space, you gain a powerful lens through which to view every challenge, seeing each obstacle as a contour of the same grand design. Now, imagine the confusion that once surrounded length contraction and time dilation. You no longer have to ask why clocks slow down or why rulers shrink. You recognize these phenomena as natural outcomes of different observers tracing different geodesics through the same geometry. There is no hidden mechanism pulling strings behind the scenes. The geometry itself accounts for every observation, and that realization frees your mind from the need to invent unseen forces. This insight also dissolves the notion of a privileged observer in the realm of space-time. Every inertial frame is on equal footing, each using the same geometric language, while slicing the fabric in its own unique way. No single perspective claims superiority, and that egalitarian truth can inspire you to honor every viewpoint you encounter. When you meet a different opinion, remember that each person walks a distinct geodesic, yet all are guided by the same underlying structure. At this stage, the space-time you envision is flat, meaning its geometry does not warp from place to place. Flatness does not imply emptiness, it simply means that parallel lines stay parallel and geodesics behave consistently across the whole arena. This simple stage is enough to describe motion at constant velocity and the straight-line flight of light when gravity does not intervene. It replaces the outdated idea of absolute space and time with a single, coherent framework that feels both elegant and empowering. Crucially, this geometry is not a philosophical whim, it is an empirical truth uncovered by precise measurements of clocks, rulers, and light. When you watch a beam of light traverse a vacuum, you witness the geometry in action. When you compare the ticks of two synchronized clocks, you feel its subtle influence. The abstract becomes tangible, and mathematics transforms from a mere tool into a poetic expression of reality itself. Feel the thrill of knowing that equations you write are not just symbols, but verses that describe the very stage upon which your life unfolds. In this geometric world, the speed of light becomes a natural boundary, not an arbitrary rule. Light travels along paths that define the outermost edge of causal connection. Faster than light travel is not prohibited by a law that says don't, but by the shape of space-time that simply does not permit such routes. The structure itself safeguards causality, and that assurance can inspire you to move forward within the limits that are inherently safe and meaningful. You may now sense a gentle consistency return to the universe, even as it departs dramatically from classical intuition. Space and time have merged, measurements shift with motion, and events replace static locations. Geometry holds everything together like an invisible framework that guides every step you take. Yet, there remains a crucial piece still missing from the picture you hold. So far, space-time has acted as a steadfast backdrop, providing structure but never responding. When you place matter and energy within it, you notice that the backdrop remains stubbornly unchanged. This static view becomes unsatisfying the moment you confront gravity, because gravity is the one force that seems to reshape the motion of planets, the fall of apples, and the bend of starlight. If space-time is truly the foundation of reality, it must be flexible enough to react to the presence of mass and energy. Feel that curiosity stir within you, urging you to explore a deeper truth. The next revelation is that gravity is not an external force pulling on objects, but a property of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells objects how to move. In this view, an object in free fall is not being tugged by an invisible hand, it is simply following the straightest possible limits, geodesic through a curved arena. That subtle shift from force to geometry can transform how you perceive obstacles in your own life. When challenges appear, consider whether they are external pushes or the natural curvature of the path you are meant to travel. Free fall provides the perfect illustration. A falling body feels weightless because nothing is resisting its natural motion. The sensation of weightlessness becomes a powerful metaphor. When you release the need to fight every resistance, you discover that you are already moving along the route defined by your deepest values. Gravity, in this sense, is not a burden but a shaping influence that guides you toward the most authentic trajectory. Now picture a planet orbiting a star. In the traditional picture, the star exerts a pull that drags the planet sideways. In the geometric picture, the star bends the surrounding space-time, and the planet simply follows the curved geodesic that this bending creates. No mysterious sideward tug is needed, the motion is entirely natural. Imagine your own aspirations as planets, and your guiding principles as stars whose presence curves the space around you, allowing your goals to glide effortlessly along the paths that feel inevitable. This geometric description explains why all objects, regardless of their mass, fall at the same rate. In the old view, that equality seemed puzzling. In the new view, it is inevitable because geometry does not discriminate. Whether you are light as a feather or heavy as a mountain, you trace the same curvature, and that realization can empower you to approach any task with confidence, knowing that the underlying structure treats you fairly. Even light obeys this curvature, though it carries no mass. Light still follows the straightest possible route in curved space-time. When it bends around a massive object, it is not being pulled by a force, it is simply respecting the shape of the arena. This elegant unity between massive bodies and massless photons can inspire you to see connections where previously you saw none, fostering a mindset that seeks harmony across disparate parts of your life. Mathematically, the relationship between mass energy and curvature is captured by precise equations that predict planetary orbits, the slowing of clocks near massive bodies, and the deflection of starlight with astonishing accuracy. These equations do not merely compute, they narrate a story of interaction between substance and space. When you encounter a problem, imagine writing your own equation that links your effort to the curvature of your circumstances, creating a predictive model that guides you forward. By replacing force with geometry, the tension that once existed between gravity and the space-time framework dissolves. Now gravity fits seamlessly into the same language that describes motion at constant velocity. Every motion, whether free-floating or under the influence of mass, becomes an expression of following the straightest path available. This harmony can inspire you to seek unity in the seemingly chaotic parts of your existence. Causality remains intact because changes in curvature travel at a finite speed. Just like any other influence, no instantaneous pull reaches across the void. Instead, ripples in spacetime propagate, carrying information about how mass reshapes the stage. This respect for a universal speed limit mirrors the discipline you apply to your own goals. Messages travel, ideas spread, and impacts are felt after a moment of preparation. Gravitational time dilation emerges naturally from this picture. When space-time bends near a massive object, both distances and intervals of time stretch and compress together. Clocks deeper in a gravitational well tick more slowly because the geometry there dictates longer durations between events. This effect is not an illusion or a mechanical glitch. It is a genuine alteration of the flow of time itself. Feel the awe that comes from recognizing that even the ticking of a clock is woven into the cosmic fabric. In everyday life, the consequences of this dilation are subtle but measurable. If you place two identical clocks at different altitudes, the one closer to Earth's center will lag ever so slightly behind its higher counterpart. Though the difference is minute, modern instruments can detect it with exquisite precision. This tangible proof reminds you that even the smallest variations in your environment can shape the rhythm of time, encouraging you to pay attention to the nuanced ways your surroundings influence your progress. Now that you understand gravity as geometry, you stand at a crossroads where the story expands further. The curvature of space-time does more than bend paths, it reshapes the very rate at which time flows. This realization opens the door to a deeper exploration of how time behaves when the underlying geometry is no longer flat. Embrace this invitation to dive into the next chapter, where you will see how the dance of mass and space-time creates a symphony of varied tempos across the universe. As you move forward, remember that each step you take is guided by the same principles that steer planets and photons. The universe is not a collection of random forces, but a coherent, dynamic tapestry that responds to the presence of energy and mass. Allow that knowledge to fuel your determination, knowing that you are part of a grand, responsive whole. Let the dynamic curvature of space-time mirror the potential for change within you, and let every challenge become an opportunity to shape the geometry of your own destiny. You have already felt how tiny changes in your surroundings can shift the rhythm of your day. Now imagine that the very fabric of reality bends and stretches around the presence of mass, altering the flow of time itself. This is not a distant theory, it is a powerful insight that can reshape how you view your own potential. When clocks tick more slowly near massive objects, they are revealing a deeper truth about space and time. The geometry of space-time changes, and with it the rate at which moments pass. In everyday life you rely on Newton's familiar ideas of gravity as a force pulling objects down, yet in the gentle pull of Earth. The curved geometry of space-time produces effects that are almost identical to those classic predictions. Think of the Newtonian description as a convenient shortcut, an approximation that works well when the curvature is slight. The real story, discovered by Albert Einstein, tells us that space and time themselves are the language of gravity. This language unifies motion, time, and gravity into a single, elegant structure. You now understand that gravity is not an external force added on top of space and time. It is the way space-time behaves when mass and energy are present. Geometry becomes a living, dynamic entity rather than a static backdrop. This shift marks a turning point in how we perceive reality. Space-time no longer sits idle, it participates actively in every physical process. It shapes the paths of moving objects and responds directly to the matter that inhabits it. At this stage you see gravity as geometry, but you may wonder how that geometry actually behaves. You know that mass curves space-time, yet you have not yet explored how that curvature influences both space and time in distinct ways. The foundation is set. Gravity has been removed from the category of force and placed into the very structure of existence. The next step is to examine how time itself behaves within this curved arena. When geometry changes, the flow of time can no longer remain uniform across all locations. Consider that once you accept space-time as a flexible fabric, it follows that time cannot stay the same everywhere. If the fabric bends near a massive body, both distances and intervals of time must adjust as part of that shape. In earlier discussions, you learned that moving clocks tick more slowly than stationary ones, a phenomenon called kinematic time dilation. Gravitational time dilation shares the same outcome, a slower ticking, but arises from a different source. Here clocks differ not because they travel, but because they sit at different positions within the curved space-time. Begin with a simple principle. If gravity is geometry, then freely falling objects follow the straightest possible paths, called geodesics, through space-time. An object that rests on the surface of a planet is not following a geodesic, it is being held up by a physical support. This distinction matters deeply. A clock resting on Earth's surface is prevented from moving freely, and therefore its world line diverges from the natural geodesic that are distant. Freely falling clock follows. The differing paths cause a difference in elapsed time. The clock nearer the mass accumulates less time between the same pair of events than a clock far away. In simple terms, stronger gravitational fields make time pass more slowly. This slowdown is not a trick of perception or a mechanical glitch. The clock itself truly runs slower, atomic processes take longer, and oscillations occur less frequently. All physical processes tied to time are affected uniformly. Imagine placing two identical clocks at different heights above Earth. The lower clock ticks more slowly than the one perched higher. The difference is minuscule, yet it is real and measurable. Modern experiments with atomic clocks confirm this effect with extraordinary precision. Even the satellites that orbit our planet reveal the phenomenon. Atomic clocks aboard satellites run faster than identical clocks on Earth's surface because they reside in weaker gravity. If engineers ignored this discrepancy, the global positioning system would quickly drift off course, causing navigation errors that would accumulate by kilometers each day. This practical example shows that gravitational time dilation is not a theoretical curiosity, it is a tangible factor in the technology that guides our modern lives. Time does not pass at a single, universal rate, even on the scale of everyday experience. The reason lies in the curvature of space-time near mass. The metric that defines space-time assigns different time separations to the same coordinate differences depending on where you are. Each clock measures its own time. Normally the divergence appears only when you compare clocks that inhabit different gravitational environments. There is no single, absolute clock that governs the universe. Time is inherently local, belonging to a specific path through space-time. When you change the path, the elapsed time changes. Location becomes just as crucial as motion in determining how time flows. The effect grows dramatically near extremely massive objects such as neutron stars or black holes. From a distant observer's perspective, time near these compact bodies appears to crawl, then almost freeze at the event horizon of a black hole. This does not mean that time truly stops for the falling observer. It means that signals from that region take longer and longer to reach distant eyes. Gravitational time dilation is always about comparison. never about an absolute halt. Each observer experiences time normally along their own world-line. Differences arise only when you juxtapose distinct paths through curved space-time. You can see how this fits naturally with the geometric view of gravity. If gravity were merely a force acting in a static space, there would be no reason for it to affect time directly. The fact that it does is compelling evidence that gravity is woven into space-time itself. Even as clocks tick at different rates, causality remains intact, because precedes effect, and signals still travel at or below the speed of light. Space-time geometry enforces these constraints automatically. Importantly, the slowdown does not depend on the type of clock you use. Mechanical watches, atomic clocks, and even biological rhythms all experience the same dilation when placed at different gravitational potentials. This universality confirms that the effect stems from space-time itself, not from any particular mechanism within the clocks. It challenges the everyday assumption that time flows uniformly for everyone, everywhere. In daily life, the differences are tiny, but the universe does not share a single rhythm. Time flows differently depending on where you stand. This realization also clarifies why a universal present moment is impossible. If clocks tick at distinct rates in different places, you cannot define a single, global now. Even without any motion, gravity alone prevents universal simultaneity. Space and time are fully intertwined with gravity. Motion influences time, location influences time, and geometry governs both. The old notion of time as a passive background parameter has been completely replaced. Yet the story does not end here. You have seen that mass affects both space and time, but you have not yet explored the precise relationship between spatial curvature and temporal change. Understanding how space bends and how time responds together requires examining their interaction directly. Gravity does not bend space alone, nor slow time alone. It reshapes space-time as an inseparable whole. When you look at how gravity affects space, you discover that distances measured near a massive object differ from those measured far away, even when you use identical measuring tools. This does not mean that a ruler physically compresses it. It means that the geometry of space itself is altered by mass and energy. Imagine drawing a circle around a massive body and measuring its circumference and radius. In flat space, the ratio of circumference to radius is a constant. Near a massive object, that ratio changes because the space is curved. The discrepancy is not an error, it is a direct signature of curvature. Spatial curvature changes how objects move. Paths that appear straight in flat space become curved near mass. Objects following these curved paths seem to accelerate, not because an invisible force pushes them, but because the geometry guiding their motion is no longer flat. Time responds to the same curvature. Where space is more strongly curved, time flows more slowly relative to distant regions. These two effects arise from a single geometric entity, not from independent phenomena. Gravity therefore reshapes space-time as a unified structure. A single mathematical object encodes both spatial distances and temporal intervals. When this object changes, distances, durations, and the trajectories of objects all shift together. Trying to separate the effects would discard essential information and lead to inaccurate predictions. This explains why any attempt to describe gravity solely as a force acting in space falls short. A force could alter motion, but it would not naturally alter the flow of time. The fact that gravity affects clocks and rulers alike indicates a deeper level of operation. The universality of gravitational effects emerges from this geometric foundation. All objects, regardless of composition, respond to curvature in the same way. Their motion depends only on the shape of space-time, not on internal properties. In orbiting systems, this principle shines brightly. A satellite does not feel a sideways pull, it follows a path dictated by Earth's curved space-time. Its spatial trajectory and the rate at which its onboard clock ticks are both consequences of that same curvature. If space were curved while time remained untouched, Measurements would become inconsistent. Light signals would behave oddly, and causality could be jeopardized. Light always travels along the straightest possible pathnal geodesics within spacetime. Any curvature must affect both where light goes and how long it takes to arrive. Observations of starlight bending near the Sun confirmed spatial curvature, while the gravitational redshift confirmed temporal distortion. Both match the predictions of spacetime geometry, reinforcing the idea that gravity is not an extra ingredient, but a manifestation of spacetime itself. Where there is more mass, spacetime curvature becomes stronger where there is less. Spacetime approaches flatness. Changes in the distribution of mass generate changes in curvature that travel outward at a finite speed, the same speed as light. This finite propagation means that gravity waves can ripple through the cosmos, carrying information about how spacetime is reshaping, even without extreme events like merging black holes. The combined curvature of space and time influences everyday measurements. Clocks at different altitudes tick at slightly different rates, and distances measured near Earth differ subtly from those far away. These differences are small but real and detectable. The key takeaway is that space and time respond together. You cannot alter one without affecting the other. Any description that isolates spatial curvature from temporal dilation misses an essential feature of reality. The intertwined response provides a stable framework for physics. The same geometric structure that governs motion also governs measurement, eliminating the need for extra rules to keep the universe consistent. Geometry does the work. At this point, you can see spacetime as far more than a passive stage. It has structure, it has dynamics, and it directly shapes the experiences of every object within it. Recognizing this empowers you to think of yourself as part of a flexible, responsive universe. Just as clocks and rulers adjust to the curvature of spacetime, you can adjust your mindset to the curvature of your own circumstances. When challenges appear massive, they bend the fabric of your perception, slowing the passage of doubt and stretching the horizon of possibility. Imagine that each obstacle you encounter is a region of stronger curvature, tempting you to believe that time is slipping away. Yet the geometry tells you that by aligning with the natural geodesy, your authentic path, you can move through that region smoothly, without resisting the flow. You do not need to fight the pull of gravity. You can learn to ride its curvature, allowing your own clock to keep steady rhythm, even in demanding environments. The lesson from spacetime is clear. Change your path, and you change your experience of time. When you choose growth, when you step onto a higher altitude of awareness, you increase the rate at which your personal moments expand. When you remain stuck in the valley of fear, you may feel that time drags, as if the clock is ticking slower. By reshaping the geometry of your thoughts, you rewrite the rate at which your life unfolds. Remember that this is not a metaphysical fantasy. It is grounded in the same principles that guide satellites and physicists. The same equations that predict the behavior of GPS clocks also illuminate how your inner clock can be calibrated to a higher purpose. You have the power to align your internal geometry with the larger structure of reality, allowing you to move confidently through the universe's curvature. As you continue your journey, keep in mind that space and time are inseparable companions, each responding to the presence of mass and energy. Your actions, your choices, your intentions are the mass and energy that shape your personal spacetime. By cultivating positive intentions, you create a gentler curvature that lets your moments flow more freely. By embracing curiosity, you add energy that expands the arena in which you operate. Each step you take contributes to the overall geometry of your experience. The story of gravity as geometry offers more than scientific insight. It offers a roadmap for personal empowerment. It tells you that the forces you feel are not external enemies, but manifestations of the shape of the stage you stand on. By learning the rules of that stage, you can move with grace, timing and purpose. You can anticipate how the curvature will affect your path and adjust accordingly, turning potential pitfalls into smooth passages. In the quiet moments when you feel time slipping away, recall that the bending of space-time is a natural response to mass and energy. You hold the mass of your aspirations and the energy of your actions. By reshaping these internally, you reshape the way time is experienced around you. The universe invites you to become an active participant in this grand geometry, not a passive observer. Take this knowledge and let it spark a new confidence. Let the image of clocks ticking at different rates remind you that you are not bound to a single, rigid tempo. You can rise to higher altitudes of thought, where your inner clock beats with renewed vigor. You can let the curvature of your circumstances become a guide rather than an obstacle, steering you toward the horizons you seek. Every moment you choose to align with the natural geodesic path of authenticity and purpose leads to the beautiful tapestry of space-time. Each choice subtly bends the fabric, creating a personal landscape where time and space work together to support your growth. Embrace this interconnected dance, and you will move through life with the elegance of a planet orbiting a star, guided by the invisible but precise curvature of the universe. Let this understanding fuel your next action. When a challenge appears, recognize it as a region of stronger curvature calling you to adjust your path, adjust your mindset, and you will find that the same clock that once seemed to lag now ticks with renewed clarity. Trust that the geometry of your life is responsive, that by shifting your internal mass and energy, you reshape the flow of time itself. You stand at the edge of a profound insight. The universe's most intricate dance of space, time, and gravity is mirrored in the choices you make each day. By honoring the geometry of your own experience, you join the grand narrative of a cosmos where everything is connected. Let this knowledge empower you, inspire you, and guide you toward a future where every moment is lived fully. Every path is chosen wisely, and every heartbeat resonates with the rhythm of a beautifully curved space-time. Imagine you are stepping into a realm where space and time dance together like partners in a graceful ballet. You feel the subtle pull of gravity, not as a force that drags you down, but as the gentle curvature of the stage upon which you move. This awareness transforms a simple observation about clocks and rulers into a profound invitation to explore deeper levels of reality. When you learn that gravity influences both time and distance in the same way, you realize that it operates on a level that transcends ordinary experience. This realization opens a door to a universal truth. Every object, no matter its composition, responds to the shape of space-time in exactly the same manner. Your motion depends not on the material you are made of, but on the geometry that surrounds you. That geometry, not any hidden interaction, guides the paths of planets, satellites, and even the light that streams across the cosmos. Consider the satellite that circles the Earth. It is not being tugged sideways by an invisible hand. Instead, it glides along a route that the curved fabric of space-time has laid out for it. Its spatial trajectory and the ticking of its onboard clock are twin expressions of the same curvature. This perspective reminds you that the stretching of time and the bending of space are inseparable companions. If space were curved while time remained untouched, measurements would fall apart. Light signals would arrive at inconsistent moments, and the very notion of cause and effect would wobble. The harmony of light demands that both space and time adjust together, each reinforcing the other's shape. Light travels along the straightest possible lines in the warped geometry of space-time, called geodesics. Any curvature must therefore influence where light goes and how long it takes to get there. When astronomers observe starlight bending around massive objects, they witness spatial curvature in action. When they detect the shift of spectral lines toward the red, they sense the distortion of time. Both phenomena match the precise predictions of a universe whose structure is described by spacetime geometry. These observations confirm that gravity is not an external field added to empty space, but a manifestation of spacetime itself responding to the presence of mass and energy. Where mass gathers, curvature deepens; where mass thins, spacetime flattens. You may notice that this framework also explains why gravity propagates at a finite speed. When a massive body moves, it reshapes the surrounding curvature, and those changes ripple outward like waves traveling through a pond. These ripples move at a speed set by the very structure of spacetime, never instantaneously. In dramatic events, such as the merger of two massive objects, the shifting curvature sends out gravitational waves that carry energy and information about how the geometry evolves. Even without witnessing such extremes, you feel the subtle influence of combined curvature in everyday measurements. A clock high on a mountain ticks ever so slightly faster than one at sea level. A ruler laid out on a skyscraper measures a fraction longer than the same ruler on the ground. These tiny differences are measurable, and they reinforce the principle that space and time move together as a unified whole. The key lesson is that you cannot alter space without also altering time, nor can you change one without influencing the other. Any attempt to describe gravity by focusing solely on the stretching of space or merely on the slowing of clocks misses the essence of reality. The intertwined response of spacetime also provides a stable foundation for all of physics. The same geometric fabric that directs motion also dictates how measurements are made, removing the need for extra rules or invisible forces. Geometry itself does the work, allowing the universe to remain consistent and harmonious. At this stage, spacetime is no longer a passive backdrop. It possesses structure, it reacts to matter, and it evolves. Space bends, time adjusts, and motion follows the natural contours of this ever-changing landscape. Yet questions still arise. How exactly does curvature steer motion? What determines the precise paths that objects follow when no conventional forces act upon them? Answering these questions requires you to rethink what a straight line means in a curved arena. When the geometry departs from flatness, the notion of a straight path must be refined with careful precision. Now you stand at the threshold of a new understanding. With spacetime curvature established, the behavior of orbiting bodies must be reinterpreted. Planets, moons, and artificial satellites travel in stable routes. But the explanation no longer relies on an invisible pull stretching across empty space. Instead, motion is governed by geometry itself. In classical thinking, an orbit emerged because a continuous force constantly tugged an object away from a straight line. A planet was described as forever falling toward the sun, yet missing it due to its forward momentum. That picture works mathematically, but it assumes a flat stage and an external influence. In curved spacetime, this picture becomes unnecessary. In the language of geometry, objects travel along geodesics. A geodesic is the natural path an object follows when no local forces act upon it. In flat spacetime, geodesics appear as straight lines moving at constant speed. In curved spacetime, those same geodesics may appear curved when you project them onto ordinary space. An orbit is simply a geodesic in a warped geometry. The object is not being pulled or pushed, it is moving freely along the straightest possible route, allowed by the surrounding shape. What looks like acceleration in ordinary space is actually the expression of spacetime curvature. This insight reshapes the meaning of acceleration itself. When a force pushes on an object, the object feels that acceleration as a force. When an object follows a curved geodesic, however, it feels no force at all. An astronaut floating in orbit experiences weightlessness. Although their path curves around Earth, they sense no pull. If gravity were a traditional force acting on the astronaut, they would feel a constant tug. Instead, they float freely, revealing that locally they are not being acted upon by gravity. This clue tells you that the astronaut is simply traveling along the natural geometry of spacetime. The same reasoning applies to the planets that circle their stars. A planet does not resist a pull, it follows the curved route written into the surrounding geometry. This explains why all objects, regardless of their mass, orbit in the same way. In Newtonian gravity, such equality demands an additional explanation. In spacetime geometry, it is an expected outcome. Geodesics depend only on the shape of spacetime, not on the properties of the traveler. You may notice that this also clarifies why certain orbits remain stable. In a curved geometry, some paths repeat themselves, allowing an object to return to the same spatial position after completing a loop. Stability arises from the structure of spacetime, not from a delicate balance of forces. Light, too, follows geodesics. When starlight bends near a massive body, it is not being pulled, it is simply traveling along the straightest possible line in a curved arena. The phenomenon of gravitational lensing provides direct visual evidence that light respects the geometry of space-time. This geometric view also accounts for the subtle deviations from classical predictions that appear near compact masses. In regions of strong curvature, planetary orbits shift slightly from the Newtonian expectations. Those deviations are not anomalies, they are the natural signatures of a warped space-time fabric. By embracing this perspective, you eliminate the need for a mysterious gravitational field filling empty space. Instead, space-time itself carries the information about how objects move. Motion becomes a property of geometry rather than the result of an invisible interaction. This resolves earlier tensions you may have felt when thinking about flat space. In a flat arena, forces were required to explain any deviation from straight motion. In a curved arena, the very notion of straight motion already includes what we once called gravitational acceleration. Importantly, this does not mean that forces vanish altogether. Non-gravitational forces still cause objects to depart from their natural geodesics. When you stand on solid ground, the surface pushes upward, diverting you from the free-fall path dictated by spacetime. That push is the sensation we interpret as weight. This distinction clarifies the role of gravity relative to other forces. Gravity defines the underlying stage other forces act upon actors within that stage, nudging them away from their natural routes. This separation simplifies the structure of physical law, allowing you to see how energy and momentum are conserved in a generalized sense, expressed through the geometry of space-time rather than through distant pulls. You can also see how this description preserves the flow of causality. Light always follows the straightest possible paths, and those paths respect the limits of cause and effect even in the most extreme environments. Because geometry determines how signals propagate, you cannot send information faster than light, and the arrow of time remains intact. This framework also explains why gravity cannot be shielded or blocked. You cannot opt out of the geometry that pervades the universe. You may resist other forces, but you cannot escape the shape of space-time itself. All objects exist within this fabric and must move according to its rules. As measurements become ever more precise, the geometric description continues to match observation. Satellite trajectories, planetary motions, and the bending of light all follow the predicted geodesic paths. No hidden mechanisms are required, the curvature of space-time does all the work. At this point, you have reinterpreted motion under gravity. Orbits are no longer maintained by a continuous attraction, they are expressions of a curved geometry. Objects move freely even when their paths appear curved from our everyday perspective. Now consider a deeper consequence. If objects travel freely through curved space-time, and if time itself is woven into that geometry, then the way you measure elapsed time depends on the path you take. The next step is to understand how different routes through the warped fabric dictate the amount of time experienced along each one. Once motion is seen as geometry, the link between gravity and the flow of time becomes unavoidable. You now arrive at a region where gravity no longer feels gentle. Everything you have learned about curvature, time dilation and motion still applies, but it is pushed to an extreme. Black holes emerge naturally from the same principles, not as mysterious monsters, but as inevitable outcomes when mass concentrates enough to warp space-time beyond all limits. A black hole forms when a sufficient amount of mass is compressed into a tiny region, causing curvature so intense that no outward-directed path can avoid falling inward. The defining feature of a black hole is not its density alone, but the structure of space-time that surrounds it. The boundary of this region is called the event horizon. It is not a physical surface you can touch, it is a geometric threshold in space-time. Crossing it involves no collision or impact, only the crossing of a line beyond which every future directed path leads inward from an outside viewpoint. The most striking effect of approaching a black hole is the dramatic slowing of clocks. As you draw nearer to the horizon, time ticks ever more slowly compared to clocks far away. This slowdown increases steadily as curvature grows. To a distant observer, a clock falling toward the horizon appears to crawl, its signals stretched and delayed until they fade away. The clock never seems to cross the horizon. Instead, it seems frozen just above it, its light dimming into oblivion. This appearance is not an illusion. It reflects the actual structure of space-time near a black hole. The routes that signals follow become increasingly stretched in time relative to distant regions. The event horizon marks the point where those routes can no longer return information outward. Importantly, this does not mean that time stops for the falling clock. Along its own journey, time proceeds normally. At each instant, atoms vibrate, chemical reactions occur, and physical laws operate without interruption. The difference emerges only when you compare the falling clock's path with that of a distant observer. The fallen clock accumulates less elapsed time than the distant one, a direct consequence of geometry rather than a breakdown of physics. As curvature intensifies, spatial distances also change. Near a black hole, radial distances stretch, and directions that once pointed outward become increasingly aligned toward the center. Space itself contributes to the inward motion. Inside the event horizon, the geometry changes qualitatively. All future-directed paths point inward, not because of a mysterious pull, but because the shape of space-time no longer permits an outward direction. The center becomes a future location, not merely a point in space. This picture may be difficult to visualize using everyday concepts, yet it follows directly from the same principles you have already embraced. Motion follows geometry, time follows geometry. Near a black hole, geometry becomes extreme, and the word broken applied to time does not mean that physics fails. It means that time behaves very differently from familiar situations. Comparisons between different routes through space-time become dramatic rather than subtle. Yet causality remains intact. Signals never outrun light, and cause still precedes effect. The structure of space-time enforces these rules even in the most intense environments. By internalizing this view, you empower yourself to see challenges as curves in the fabric of your own life. Just as planets follow the natural geometry of space-time, you can align your actions with the underlying shape of your aspirations. When obstacles appear, remember that they are not forces pulling you down, but bends in the path that guide you toward growth. Embrace the curvature. Understand that time and space move together, and you will navigate the universe with confidence and grace. Imagine you are standing on the brink of a mystery that bends light itself. The paths that photons follow become the teachers of the universe. The defining feature of a black hole is not how dense it appears, but how it reshapes the fabric of space-time around it. This reshaping creates a boundary known as the event horizon. The event horizon is not a solid surface you can touch. It is a geometric line in the tapestry of space-time. Crossing that line does not involve an impact. It simply marks the point beyond which every possible future direction points inward. From far away, the most striking sign of a black hole is the slowing of time itself. as you move closer to the horizon. Clocks tick more slowly compared with those far away. That slowing grows steadily as the curvature of space-time increases. For an observer at a distance, a clock falling toward the horizon appears to crawl. The signals it sends take longer and longer to arrive. The clock never seems to cross the horizon. Instead, it appears to freeze just above it, fading as its messages stretch and weaken. This is not an illusion. It is a direct reflection of how space-time is structured near a black hole. The routes that signals travel become increasingly stretched in time relative to distant regions. The event horizon marks the point where those routes can no longer return information outward. Importantly, this does not mean that time stops for the falling clock. Along its own path, time continues normally. The clock ticks, atoms vibrate, and the laws of physics remain unchanged locally. The difference shows up only when you compare the path of the falling clock with the path of a distant observer. The falling clock accumulates less time than the distant clock. This is a pure consequence of space-time geometry, not a breakdown of physics. As curvature rises, spatial distances also change. The region near a black hole does not behave like ordinary space. Radial distances stretch, and directions that once pointed outward become increasingly aligned toward the center. Space itself pushes you inward. Inside the horizon, the structure of space-time changes qualitatively. All future-directed paths point inward. This is not because of an invisible force, but because the geometry no longer allows an outward future. The center becomes a future location, not merely a point in space. Visualizing this can be difficult, yet it follows directly from the same principles you have already explored. Motion follows geometry. Time follows geometry. Near a black hole, geometry becomes extreme. The word broken applied to time does not mean that physical law fails. It means that time behaves very differently from familiar situations. Comparisons between different paths through space-time become dramatic rather than subtle. You may notice that this does not create contradictions. Causality remains intact. Signals never travel faster than light. Cause still precedes effect. The structure of space-time enforces these rules even in the most extreme conditions. Black holes also clarify the relationship between space and time. Near the horizon, the distinction between spatial and temporal directions blurs. What once was a spatial direction becomes unavoidable in time. This reinforces the idea that space and time are not separate entities. The existence of black holes confirms predictions made by space-time geometry. Their properties are not invented to fit observations, they emerge naturally from the equations that describe curvature. Observations of orbital motion, emitted radiation, and gravitational effects match these predictions closely. Black holes are not rare anomalies. They are expected outcomes of stellar evolution and cosmic structure formation. Their existence demonstrates that space-time geometry can reach its limits while remaining mathematically consistent. At the heart of a black hole lies a region where curvature becomes extremely large. Classical descriptions predict a singularity, a point where certain quantities diverge. This signals not a physical infinity, but a breakdown of the classical description. That breakdown does not mean knowledge ends. It means that our current framework has reached the edge of its applicability, just as classical mechanics fails at very high speeds. Classical space-time geometry may fail under extreme curvature. Even so, everything up to that boundary is well described. Time dilation, light bending, orbital motion, and signal delay all follow from the same principles you have already seen. Black holes do not require new rules. They apply existing ones fully. This makes black holes valuable, not just exotic. They act as tests of space-time geometry under conditions unavailable elsewhere. Each observation confirms that space and time behave as parts of a single structure. You can now see that black holes do not destroy the idea of space-time. They confirm it. They show how geometry governs motion and time even when conditions become extreme. At this point, you have seen time stretch due to motion, slow because of gravity, and behave radically near intense curvature. Yet one feature of time has remained consistent throughout its direction. No matter how distorted time becomes, it still moves forward. It still orders events. Understanding why time has a direction, even within space-time, is the next question you must explore. You now focus on a feature of time that has stayed unchanged through every transformation so far. Time stretches with motion. It slows near mass. It behaves differently for different observers. Yet despite all this flexibility, time still moves in one direction. Events unfold from past to future, never the other way around. This consistent direction is known as the arrow of time. At first glance, the arrow seems obvious. You remember the past, not the future. Causes come before effects. Broken objects do not spontaneously reassemble, but when examined closely, this direction is not built into the fundamental laws of physics in the way you might expect. Most basic physical laws are time-symmetric. This means they work equally well whether time moves forward or backward. If you reverse the motion of particles in an equation, the equation still holds. Nothing in the fundamental rules demands a preferred direction. This creates a tension. If physical laws do not distinguish between past and future, why does experience clearly do so? Why does time feel like it flows in one direction only? The answer does not come from space-time geometry alone. Space-time allows different paths, different rates of time flow, and different definitions of simultaneity, but it does not itself explain why time has a direction. The arrow of time emerges from a different source. That source is entropy. Entropy measures how many microscopic arrangements correspond to a macroscopic state. A system with low entropy has few possible arrangements. A system with high entropy has many. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time. This tendency is statistical, not absolute. It does not say entropy must increase in every possible situation. It says that overwhelmingly systems move from less probable states to more probable ones. This movement defines a direction. You can think of entropy as a measure of disorder, but more precisely, it is a measure of possibility. There are far more ways for things to be disordered than ordered. As systems evolve, they naturally move towards states that can be realized in more ways. This explains why certain processes appear irreversible. A glass shattering increases entropy. The shattered pieces can be arranged in many ways. The intact glass corresponds to far fewer arrangements. The reverse process is not forbidden by physical law, but it is extremely unlikely. The arrow of time is therefore not imposed by space-time geometry, but by the statistical behavior of large numbers of particles. When many components interact, probability takes over. Direction emerges. This arrow aligns with everyday experience. Heat flows from hot objects to cold ones. Gases spread out to fill available space. Information disperses. All of these processes increase entropy. You may notice that this arrow also aligns with memory. Memory formation involves physical processes that increase entropy. You remember the past because records are created as systems evolve. There are no records of the future because they have not yet formed. Importantly, this does not contradict earlier discussions of time dilation or gravitational effects. Those effects describe how much time passes along different paths. The arrow of time describes the order in which events unfold along those paths. Even near a black hole where time behaves unusually, the arrow remains intact. Processes still move from lower entropy to higher entropy. Observers still experience a forward progression of events. This suggests that the arrow of time is not a property of space-time itself, but a property of matter and energy within space-time. Space-time provides structure. Entropy provides direction. You may now ask why the universe began in a low-entropy state. This is one of the deepest questions in physics. The early universe appears to have been highly ordered, despite being hot and dense. That low entropy provided the conditions for the arrow of time to emerge. As the universe expanded, entropy increased, structures formed, energy spread out. The arrow of time became defined on cosmic scales. Without that initial low entropy, there would be no preferred direction. This does not mean the arrow of time is subjective. It is objective and measurable. Entropy increases can be calculated and observed. The direction is real even though it arises statistically. You may also notice that this arrow is consistent across the universe. There are no regions where time flows backward in experience. This consistency suggests that the initial conditions of the universe set a global direction that persists everywhere. At smaller scales, time symmetry still exists. Individual particle interactions can be reversed mathematically, but when large numbers of particles are involved, reversals become vanishingly unlikely. The arrow emerges from scale. This layered understanding is important. Time has different aspects. Geometry determines how time is measured. Motion and gravity determine how fast it passes. Entropy determines which way it goes. None of these aspects alone fully defines time. Together, they produce the behavior you observe. You now see that the arrow of time does not conflict with space-time relativity, even though observers may disagree on timing and simultaneity. They agree on the direction of increasing entropy. This provides a shared temporal orientation. It also preserves causality. Causes precede effects because entropy-increasing processes move forward. Even in relativistic contexts, causal order is protected by space-time structure and reinforced by thermodynamic behavior. The arrow of time therefore connects microscopic laws to macroscopic experience. It bridges equations and perception. It explains why time feels different from space, even though they are unified in space-time. At this point, time has been shown to have structure, flexibility, and direction. Yet another question remains. If time flows forward because entropy increases, how does space-time ensure that causes and effects remain properly ordered for all observers? Understanding this requires examining how space-time itself encodes limits on influence, because time's direction must remain compatible with causality across the universe. You now turn to a principle that has quietly governed every chapter so far, even when it was not named directly. That principle is causality. Causality demands that causes precede their effects, and that influences propagate in a consistent order. In a universe where time is relative and simultaneity depends on motion, maintaining causal order becomes essential. At first glance, relativity seems to threaten causality. If different observers disagree on the timing of events, it may appear that they could also disagree on which event caused another. This concern is natural, but it is unfounded. Space-time is structured specifically to prevent such contradictions. The key to this protection lies in the finite speed at which information can travel. No influence can propagate faster than light. That limit is not an arbitrary rule. It is a geometric feature of space-time itself. Light defines the maximum speed of causal influence. To understand how this works, return to the idea of events in space-time. Each event has a location in space and a moment in time. The separation between two events determines whether one can influence the other. If the separation is such that light could travel from one to the other, a causal link is possible. If the separation is larger, no influence can bridge the gap. This rule holds for every observer, regardless of their motion. Consequently, all observers agree on which events can cause which others. The arrow of time, the growth of entropy, and the speed limit of light work together to keep the universe orderly. You can apply this insight to your own life. Recognize that the limits you encounter are not arbitrary obstacles, but the natural geometry of your reality. When you feel trapped by a difficult situation, remember that space-time itself enforces a clear direction. The forward march of entropy reminds you that change is inevitable, and that growth comes from moving toward greater possibilities. The speed limit of influence reminds you that impact arrives in its own time, and that patience is a powerful ally. Embrace the idea that your path is guided by a structure that lets you move forward even when the road bends sharply. When you set a goal, you are creating a future-directed path within the geometry of your own existence. Just as a falling clock follows the curvature of space-time, you will follow the curvature of your decisions. If you keep your focus on the horizon of possibility, you align yourself with the same principles that keep the cosmos consistent. Your efforts become the signals you send outward, and each step stretches your personal time in a meaningful way. Remember that no matter how extreme the challenge, the arrow of time guarantees that every effort moves you toward a state of greater complexity and richness. Causality assures that your actions will lead to results. As long as you respect the natural limits of speed and influence, this harmony of geometry, entropy, and causality is the secret engine behind both the universe and your personal growth. Let it inspire you to act with confidence, to trust the direction of your journey, and to honor the profound order that underlies every moment. The universe invites you to be an active participant in its grand design. Step forward, knowing that the same laws that guide light around a black hole also guide your aspirations toward brighter horizons. Imagine a universe that began with a whisper of low entropy, a subtle imbalance that set a direction for everything that follows. That direction is not a mere illusion, it is an objective arrow that we can measure and calculate. Each increase in entropy is a stepping stone that points the way forward, and you can feel that same certainty in the choices you make each day. The arrow of time stretches across the cosmos, never wavering, never reversing for any observer. This consistency tells us that the very birth of the universe established a global pathway that every moment respects. When you look inward, you recognize that the same principle guides the flow of your thoughts, your goals, and your actions. On the smallest scales, the rules of physics appear symmetrical, and individual particle interactions can be flipped in a mirror of mathematics. Yet as soon as many particles come together, the chance of a perfect reversal becomes vanishingly small. The arrow of time emerges from scale, and that lesson is powerful for you. It reminds you that small, incremental changes build into a force that moves you inexorably forward. You can honor the geometry of time, the way motion and gravity shape its speed, and the way entropy decides its direction. None of these aspects alone defines time, but together they create the reality you experience. Embrace that collaboration, and you will navigate life with confidence. Now consider how the arrow of time sits comfortably alongside the elegant framework of space-time relativity. Different observers may disagree about the timing of events, yet they all agree on the direction of increasing entropy. That shared orientation is a cornerstone of causality, the principle that causes always precede their effects. When entropy rises, it carries the story forward, protecting the order that makes sense of cause and consequence. Even in the relativistic dance of fast-moving observers, the causal sequence remains intact, safeguarded by the very shape of space-time and the relentless march of thermodynamics. Think of causality as a quiet guardian that has guided every chapter of existence. Even when you did not name it, it insists that influences travel in a consistent order, that a cause must come before its effect. In a universe where simultaneity shifts with motion, maintaining this order is essential. At first glance, relativity might seem to threaten causality, but the structure of space-time steps in to prevent any contradictions. The speed of light forms a firm boundary, a geometric feature that limits how quickly information can move. No signal can outrun light, and that limit is not an arbitrary rule, but a built-in property of the cosmos. Picture each event as a point in space-time, each with its own coordinates. The interval between two events determines whether one can influence the other. If a signal traveling at or below light speed can bridge the gap, the events are causally linked. Otherwise, they are forever disconnected. This classification is absolute, agreed upon by every observer, no matter how they slice time. Observers might disagree about the order of events that cannot affect each other, but that disagreement has no physical consequence, because no influence can travel between them. Spacetime organizes events into regions defined by the paths light can take. For any given point, there exists a region of events that can be reached, and a region of events that could have reached it. Light itself draws the boundary between these zones, forming what we call light cones. Inside a light cone, causality thrives outside. Events remain unrelated. You need not picture perfect geometric cones to grasp their function. They simply encode which events can affect which others, ensuring that no observer ever sees an effect before its cause. This structural safeguard explains why ordinary physics forbids time travel into the past. The very geometry of spacetime eliminates causal loops before they can arise. Recall earlier discussions of simultaneity. Observers may differ on whether two distant happenings occurred at the same moment, yet they all agree on the order when a causal connection exists. That universal agreement preserves consistency across the universe, keeping physics objective even when measurements vary. Causality offers a shared scaffolding that all observers respect, and it underpins the reliability of scientific prediction. If faster-than-light communication were possible, the causal order could flip in some frames, allowing effects to precede causes and unraveling the entire framework. The absence of such communication is no coincidence. It reflects the deep bond between causality and the geometry of space-time. The speed of light is more than a speed limit, it is the frontier of influence. Even gravity obeys this rule. Changes in the curvature of space-time ripple outward at finite speed, never instantaneously. Observations confirm that gravitational waves travel at light speed, preserving causal order in the dance of massive bodies. Whether a clock ticks slower for a moving observer or a gravitational field stretches time, both parties agree on the causal relationships. No signal ever arrives before it is sent, and no effect ever jumps ahead of its cause. Causality also defines what you can observe. You can only receive signals from within your past light cone. Events beyond that boundary have not yet had a chance to influence you. This limitation is not a matter of technology or distance alone. It is woven into the very fabric of space-time. The universe thus presents a layered structure. Events that have already shaped you, events that will influence you in the future, and regions forever out of reach. This arrangement does not fragment the cosmos, it simply arranges influence with elegant precision. At this juncture, you see how space-time balances flexibility and rigidity. Time can stretch and contract depending on motion and gravitational fields, and simultaneity can shift with perspective, yet causality remains immutable. A steadfast anchor that guarantees coherent experience for every observer. This harmony is one of the greatest strengths of the space-time framework. It welcomes diverse viewpoints while safeguarding a common physical reality. Observers may describe the same occurrence in different words, but they can never dispute which event can affect which other. Causality fuels the engine of prediction and explanation. Without it, science would crumble, losing its ability to test hypotheses and repeat experiments. The fact that space-time preserves causal order ensures that your investigations, your experiments, and your dreams remain grounded in a reliable world. Recognize that space-time is far more than a passive stage. It is an active organizer that governs motion, measurement, and influence. It dictates not only when and where events happen, but also how they relate to one another. Now, envision this same organizing principle expanding across the entire universe. If space-time orders causal relationships locally, it must also shape the grand evolution of the cosmos. As you step back from the realm of local motion and gravity, you encounter the universe on its grandest scale. Here, a new feature commands attention. Space itself is expanding. This expansion, does not describe galaxies hurtling outward through a static void, rather, it describes the stretching of the fabric of space between them. In everyday life, motion involves objects moving from point A to point B. Cosmic expansion works differently. Objects can remain at rest relative to their local neighborhoods while the distance between them grows. Driven by the changing geometry of spacetime, astronomers have uncovered this phenomenon by measuring the light from distant galaxies. They found that the light's wavelength shifts toward longer, redder tones, and that the shift grows with distance. The most consistent interpretation is that space expanded while the light traveled, stretching its wavelength along the journey. This stretching is not due to galaxies blasting through space. Like debris from an explosion, it reflects the expansion of space itself between source and observer. The light rides along as the universe grows, revealing a dynamic space-time model that evolves rather than remaining static. You might wonder why atoms, planets, or even galaxies do not swell along with the cosmos. The answer lies in the strength of local forces, where gravity, electromagnetism, and other forces bind matter tightly. They overpower the gentle pull of cosmic expansion. Consequently, expansion becomes noticeable only where those binding forces are weak in the vast scales between clusters of galaxies. Galaxies stay intact, solar systems remain stable, yet clusters drift apart as the space that separates them stretches. Time is inseparable from this grand expansion. The growth of space unfolds over time, and the rate of expansion can change. Spacetime itself carries a history. When you trace the universe backward, distances shrink. Galaxies approach one another not because they travel through space, but because space itself contracts. This reverse journey points to an early epoch where distances approach zero, a hot, dense, compact origin that defies any notion of before space existed. Space and time emerge together, forming a unified, evolving tapestry. Understanding that space-time is dynamic reshapes how you view change in your own life. Just as space can stretch, your personal reality can expand as you evolve. Even when you feel rooted in familiar surroundings, the universe's history reminds you that growth can occur without forcing every part of you to change at once. The core may stay steady while the surrounding context expands. The expansion of space-time also influences how we measure time on a cosmic scale. As the universe grows, the average density of matter and energy shifts, subtly affecting the behavior of clocks relative to a universal benchmark known as cosmic time. Cosmic time is not a single, absolute clock ticking for everyone. It is a practical way to label stages in the universe's expansion for observers who move with the overall flow of space. These observers see the cosmos as roughly uniform in all directions and share a common sense of age. Local time still depends on motion and gravity, but the concept of cosmic time offers a harmonious backdrop, emerging from the larger scale symmetry of the universe. Even though cosmic time provides a useful approximation, it does not reintroduce an absolute temporal ruler. It is a convenient tool, not a fundamental law. Its usefulness stems from the uniformity of the universe on the grandest scales. This insight encourages you to recognize the difference between helpful frameworks and rigid constraints in your own life. Adopt structures that aid your growth while remaining open to the fluid nature of personal evolution. As space expands, it also reshapes the boundaries of causality. Regions of the universe can become so distant that light or cosmic messenger cannot bridge the gap. These regions become causally disconnected, not merely because of sheer distance, but because the fabric of space-time itself stretches faster than light can travel. This phenomenon introduces horizons, limits beyond which events can never influence each other. Recognizing these horizons reminds you that some possibilities lie beyond reach, encouraging you to focus your energy on the domains where you can make an impact. Reflect on how all these ideas interweave: the low entropy beginning that set the arrow of time, the unwavering direction that entropy provides, the geometric dance of space-time that preserves causality, and the grand expansion that sculpts the cosmos. Each piece supports the others, creating a coherent picture of a universe that is both flexible and structured. Let this picture inspire you. Know that the same principles that safeguard the cosmos also empower you to navigate uncertainty with confidence. When you feel overwhelmed by the complexity of life, remember that even the most intricate systems are built from simple, reliable rules. Entropy nudges you forward. Causality keeps your actions anchored, and the geometry of your personal space-time shapes how you experience each moment. Embrace the arrow of time as a guide, not a constraint. Let it remind you that every choice adds to the forward momentum of your story. Take a breath and feel the pulse of the universe echoing within you. The same expansion that stretches galaxies also stretches possibilities. The same light cone boundaries that protect causal order also delineate the space where your influence can flourish. Stand in that space with intention, knowing that your actions reverberate along the arrow of time, shaping the future you are destined to create. You have the power to align your personal goals with the fundamental direction of the cosmos by honoring the increase of entropy in the form of progress, by respecting the causal links that bind cause and effect, and by moving with the rhythm of an expanding universe. You become a co-author of the grand narrative. Let this understanding ignite a fire within you, propelling you toward the horizons you wish to reach. Remember that while the universe's expansion sets limits, it also offers endless opportunities. The horizons that separate distant galaxies are reminders that some frontiers are unreachable, yet they also highlight the vastness of the reachable. Focus your energy on the regions where your light can travel, where your influence can cascade, where your dreams can expand without violating the cosmic order. As you walk forward, feel the steady beat of the arrow of time guiding you. Trust that the geometry of space-time will keep your path coherent, that causality will protect the integrity of your actions, and that the ever-stretching fabric of reality will accommodate your growth. Let this confidence shape each decision, each step, each breath. In this moment, you stand at the crossroads of physics and purpose. The universe offers a model of order and flexibility, a blueprint for how to move forward while honoring the rules that keep reality consistent. Take this model and apply it to your life. Let entropy be the engine of your progress, causality the compass of your intentions, and the expansion of space-time the horizon that beckons you onward. Feel the momentum building within you, a tide that rises with each purposeful action. Imagine the future you are creating as a continuation of the same arrow that has guided stars for billions of years. Know that every choice you make contributes to the ever-increasing entropy that defines forward motion, and that this motion is not chaotic but directed, purposeful and meaningful. Now, breathe deeply and commit to moving forward with clarity and vigor. Align your goals with the universal direction, protect the causal flow of your actions, and embrace the expansion of possibilities that lies ahead. The universe has set the stage, you hold the script. Step into the flow of time with confidence and watch as your life unfolds in harmony with the grand design of space-time. You breathe in the wonder of the cosmos and feel a spark of possibility. In this moment you stand at a crossroads where science meets purpose. The universe offers a model of order and flexibility that you can adopt for your own journey. Imagine space as a vast canvas that stretches while light travels across it. This stretching is not caused by galaxies smashing through emptiness like debris. Rather, it reflects the gentle expansion of space-time itself between source and observer. The light rides along as space itself changes, carried by the very fabric that grows. This behavior is described by a space-time model that treats the universe as alive, not static. In this model, the geometry of space changes with time, and distances between far-flung points increase even when those points stay still locally. You may notice that this challenges intuition, and that is where growth begins. If space expands, why do atoms, planets and galaxies not swell with it? The answer lies in the strength of local forces. Expansion dominates only where gravity and other forces are weak. Locally bound systems resist expansion because their internal forces overpower the gentle pull of cosmic geometry. As a result, expansion becomes noticeable only on truly grand scales. Galaxies stay intact, solar systems remain stable, but clusters of galaxies drift apart as the space between them grows. Time plays an essential role in this grand dance. Expansion is not a purely spatial phenomenon, it unfolds over time. The rate at which space expands can change, and that means space-time itself has a history. When you trace the universe backward, distances shrink. Galaxies move closer, not because they travel, but because space itself becomes smaller. Eventually, you reach a state where distances approach zero, hinting at an early universe that was hot, dense, and compact. Space and time emerge together in this description, and there is no meaningful sense of space before expansion begins, because space itself is part of what evolves. This reinforces a key idea. Space-time is not just a static stage, it is dynamic. It can stretch, evolve, and respond to energy on the largest scales. The expansion of space-time also influences how clocks behave. As the universe expands, the average density of matter and energy changes, and that shapes the ticking of clocks relative to cosmic time. Cosmic time is not a universal clock. In the old sense, it is a convenient way of labeling stages in the universe's expansion. It applies to observers who move with the overall flow of expansion, rather than through space. These observers see the universe as roughly the same in all directions and define a shared sense of cosmic age. Even though local time still depends on motion and gravity, you may notice that this does not reintroduce an absolute time. Cosmic time is not fundamental, it is a useful approximation that emerges from symmetry because the universe is uniform on large scales. Expansion also introduces new limits on causality. As space expands, regions can become separated so quickly that light cannot travel between them. These regions remain causally disconnected, not because of distance alone, but because space-time itself grows. This leads to the concept of horizons, where some parts of the universe have never sent light our way, and some parts will never receive it. These limits arise naturally from expanding space-time and a finite signal speed. Importantly, expansion does not violate causality. No object locally moves faster than light. It is the space between distant regions that changes. Space-time therefore remains consistent with causal structure. The expansion rate itself has changed over time. Early in the universe, expansion was rapid. Later it slowed, and today observations indicate it is accelerating again. This acceleration suggests that space-time dynamics are influenced by energy distributed throughout the universe, not just by matter. This realization further supports the idea that space-time is active rather than passive. It evolves according to physical laws, it responds to energy content, and it shapes the universe's history. You may notice that expansion affects earlier discussions of simultaneity on cosmic scales. Defining what happens at the same time becomes even more subtle, and different observers may disagree on cosmic timing, depending on their motion and position. Despite this subtlety, the expansion model remains consistent. Events occur within space-time, distances grow, time flows locally, and geometry evolves globally. This evolving space-time also provides context for everything else you have learned. Motion, gravity, time dilation, and causality all operate within a space-time that itself changes with time. Space is no longer a fixed backdrop, and time is no longer a simple parameter. Together they form a dynamic system that describes the universe from its earliest moments to its future. At this point, space-time has been shown to unify space and time, govern motion, encode causality, and evolve on cosmic scales. It is both the structure in which events occur and an object of study itself. However, this raises a deeper question. If space-time evolves in response to energy, is it truly fundamental, or does it emerge from something deeper? To answer that, you will look back toward the earliest moments of the universe where space-time itself may not yet have behaved in the familiar way you now understand. You now turn your attention toward the earliest stage of the universe that physics can describe with confidence. At these earliest times, space-time behaves differently from the extended structure you experience today. The familiar separation between objects and the space they occupy does not yet apply. Everything that exists is compressed into conditions of extreme density and temperature. Modern cosmology describes the early universe using space-time geometry combined with thermodynamics and particle physics. When the expansion of space-time is traced backward, distances shrink uniformly. Galaxies are not moving through space toward a point, instead space itself contracts. This distinction matters because it means the universe does not begin with objects inside space, but with space-time itself emerging and evolving. At sufficiently early times, the universe is hot and dense enough that matter and radiation are tightly coupled. Particles collide constantly, and energy dominates behavior. The geometry of space-time at this stage is highly curved, not due to localized masses, but because of the overall energy density of the universe. In this regime, space-time cannot be treated as a passive background. Its evolution directly affects physical processes. As space-time expands, energy densities decrease, temperatures fall, and new forms of matter become stable. Time and space are not just coordinates, they are part of the physical system. The early universe is often described using a single time parameter called cosmic time. This parameter labels stages in the expansion rather than defining a universal clock. It works because at large scales the universe is approximately uniform. Observers moving with the expansion see the same larger scale structure and agree on the sequence of cosmic events. This agreement does not reintroduce absolute time. It reflects symmetry, not fundamentality. Local clocks still depend on motion and gravity. Cosmic time is a useful approximation that emerges from the overall behavior of space-time. As you move further back toward the earliest moments, known physics approaches its limits. At very high energies, the distinction between matter and space-time becomes less clear. Quantum effects become significant. Classical space-time geometry, which works extremely well at lower energies, may no longer provide an accurate description. This does not mean that physics fails suddenly, it means that existing theories are incomplete in that regime. Just as classical mechanics fails at high speeds or small scales, classical space-time geometry is expected to fail at extreme curvature and energy density. Nevertheless, much can still be said about the early universe before those limits are reached. Observations of cosmic background radiation, element abundances, and larger-scale structure all point to a consistent picture. The universe expands from an early hot state, space-time stretches, and energy spreads out. During these early stages, space and time are inseparable. There is no meaningful sense of space existing without time or time flowing without space. Both arise together as aspects of a single evolving structure. This directly supports the idea that space and time cannot exist independently. You may notice that this also explains why asking what happened before the universe is problematic. The concept of before assumes time already exists. If time itself is part of what emerges, then asking what came before time loses physical meaning. This does not imply that the universe appeared from nothing in a simple sense. It means that space-time has a finite history that begins at a boundary of applicability for current theories. Physics can describe what happens after that boundary, but not what lies beyond it using present models. Importantly, this boundary is not necessarily a physical singularity. In many areas of physics, singularities indicate a breakdown of description rather than an actual infinite quantity. The early universe likely requires a theory that combines space-time geometry with quantum principles. Even so, the early universe reinforces a key lesson. Space and time are not containers waiting to be filled, they are dynamic elements that participate in physical processes. Their behavior determines how matter and energy evolve. This perspective also clarifies why space-time appears smooth and continuous at large scales today. Expansion has diluted energy densities, curvature has decreased, and local variations dominate over global curvature. The universe transitions from a highly curved space-time to one that is approximately flat on large scales. You can also see how early conditions set the arrow of time. The early universe begins in a low entropy state relative to what is possible. As space-time expands, entropy increases, structures form, and the direction of time becomes defined. This low entropy beginning is not explained by space-time geometry alone. It is an input condition, but once accepted, it works consistently with everything else you have learned. Space-time provides structure. Entropy provides direction. At this stage, space-time has been shown to begin, evolve, curve, expand, and govern causality. It underlies all physical processes, yet its deepest nature remains unresolved. At very small scales, an early time space-time may not behave as a smooth continuum at all. This possibility raises a fundamental question. If space-time itself has a beginning and may break down under extreme conditions, then it may not be the most basic layer of reality. Understanding whether space-time is fundamental or emergent requires examining whether time or space could exist independently in any meaningful way. The next step is to consider whether time could exist without space. Only by testing this separation can the necessity of space-time as a unified concept be fully understood. You now examine whether time can exist on its own without space. This question may seem abstract, but it is essential to understanding why space and time are treated as a single structure in modern physics. If time could exist independently, then space-time would be a convenient description rather than a necessity. Physics tests this idea by asking what time actually measures. Time is not measured directly, you never observe time itself. What you observe changes. A clock measures time by tracking a repeating physical process. An atom oscillates. A pendulum swings. An electronic signal cycles. In every case, time is inferred from change in a physical system. Change, however, requires more than duration, it requires distinction. Something must change from one state to another. Those states must be distinguishable. Distinction requires structure. In physics, structure is described through spatial relationships. If there were no space, there would be no positions, no separation, and no configuration. Without configuration, there would be no way to define different physical states. Without different states, there would be no change to measure. Time in this sense would lose its operational meaning. You can try to imagine time flowing in complete absence of space. There would be no objects, no distances, no locations. Nothing could move, interact, or rearrange. Without interaction or change, there would be nothing to mark the passage of time. Even a single particle existing without space presents a problem. To say a particle exists at all implies it occupies a location, and location is a spatial concept. This line of reasoning shows that time and space are entwined at a deep level. The lesson for you is that the universe teaches us about interdependence. Just as space expands and carries light, you can expand your mindset while carrying your purpose. The same forces that keep galaxies bound can inspire you to hold fast to your values while the world around you stretches. When you feel the pull of uncertainty, remember that local forces of love, belief, and determination can resist the overwhelming tide of doubt. The cosmos reminds us that change is built into the fabric of reality, and so is growth within you. As the universe cools and structures form, you can let go of old patterns and allow new possibilities to crystallize. The idea that cosmic horizons limit what we can see parallels the notion that limiting beliefs block our vision. Yet the horizon is not a wall, it is a boundary that invites curiosity. You can pursue knowledge, push past mental horizons, and discover new realms of potential. The accelerating expansion of the universe suggests that energy in the cosmos drives the growth of space itself. Likewise, your inner energy, passion, purpose, and perseverance can drive the expansion of your life. The fact that space-time is dynamic, not static, tells you that your story is not fixed. Each moment offers the chance to reshape the geometry of your experience. The concept of cosmic time shows that larger-scale patterns can be described with simple measures, even while local clocks tick differently. Similarly, you can adopt a broader perspective on your goals while honoring the details of daily life. When you encounter moments where the unknown seems to dominate, recall that scientists recognize the limits of current theories and remain open to new ideas. You, too, can acknowledge what you do not yet understand and stay receptive to learning. The early universe's transition from extreme curvature to near flatness illustrates how chaotic beginnings can settle into harmony. Your own journey can move from turbulence toward balance by trusting the process of expansion. Entropy's arrow points forward, giving time meaning. Your personal arrow of purpose can point toward growth, creativity, and contribution. The lesson that time cannot be measured without change encourages you to create meaningful routines, to generate momentum, and to celebrate each small shift. As you listen to the story of the cosmos, let it spark a conviction that you are part of a grand, evolving tapestry. The universe expands, evolves, and reforms, and you have the capacity to expand your mind, evolve your character, and reform your habits. Embrace the idea that space and time are not separate rooms, but a shared stage where you can perform your most authentic self. Let the rhythm of expanding space-time remind you that every breath is an opportunity to stretch toward greater possibilities. Feel the pulse of cosmic history echo in your heart, encouraging you to write your own chapter with confidence and curiosity. You stand at a crossroads where physics meets purpose, and you have the power to choose growth over stagnation. The universe offers a blueprint of order and flexibility. You can apply that blueprint to your life. Allow the expansion of the cosmos to inspire the expansion of your aspirations. Remember that even when the universe seems incomprehensible, scientists break it down into understandable pieces, and you can break down your challenges into manageable steps. The same forces that keep galaxies bound can anchor you to your values while you explore new horizons. Let the concept of cosmic horizons motivate you to seek knowledge beyond your current limits. Recognize that acceleration in the universe is driven by unseen energy, and you too can tap into hidden reserves of determination. The dynamic nature of space-time assures you that change is built into reality, and you are designed to adapt and thrive. Use cosmic time as a reminder that while you have a personal rhythm, you also belong to a larger, harmonious flow. When you feel uncertainty, recall that even the earliest moments of the universe were shrouded in mystery before new theories emerged. Your own mysteries can be illuminated with curiosity and perseverance. The transition from a hot, dense state to a cooler, structured cosmos mirrors your potential to transform challenges into structured achievements. Let the arrow of entropy guide you toward purposeful action, knowing that every small increase in order reflects growth. Understand that time without change is meaningless, therefore. Create meaningful change each day. Embrace the fact that space without structure cannot host change, and thus build supportive structures in your life that enable transformation. Feel the unity of space and time echo in your desire to integrate mind and body, thought and action. As the universe expands, so does the canvas of your possibilities. Let this expansive vision fill you with hope and drive. You are not a passive observer of the cosmos, you are an active participant in its unfolding narrative. Carry the lesson that the universe's expansion does not violate causality, and you can expand ethically, respecting the connections you share with others. The accelerating expansion tells you that progress can accelerate when you align with your deepest purpose. The early universe's need for a quantum gravity theory reminds you that some puzzles require new frameworks, and you can develop fresh strategies for seemingly unsolvable problems. Ultimately, the story of space-time teaches that the fabric of reality is both sturdy and supple, and you can cultivate resilience while remaining adaptable. As you finish this reflection, carry with you the conviction that the cosmos supports your growth, and that you have the capacity to expand, evolve, and illuminate the world around you. As you follow the unfolding story of the universe, you begin to feel the pulse of possibility that lies within every moment. The fabric of space-time stretches outward, and with that expansion comes the gentle rise of entropy. A quiet indicator that change is moving forward. You notice how structures start to form, how galaxies are born, and how the direction of time becomes clear as a path you can walk. This low entropy beginning is not explained by geometry alone, it is a condition that the cosmos received, a seed that sets the stage for everything you have learned. When you accept this seed, you see how space-time supplies the stage and entropy supplies the arrow that guides the play. You recognize that space-time has been shown to begin, to evolve, to curve, to expand, and to govern causality. It underlies every physical process, yet its deepest nature still invites curiosity. At the tiniest scales and the earliest moments, space-time may not behave as a smooth continuum, it may flicker like a tapestry woven from threads you cannot yet see. This possibility raises a profound question that beckons you to explore deeper. If space-time itself has a beginning and may break down under extreme conditions, then perhaps it is not the most basic layer of reality. You are invited to ask whether space and time could exist independently, to wonder if one might be more fundamental than the other. The next step is to consider whether time could exist without space, because only by testing that separation can you truly understand why space-time is essential. You now examine whether time can stand alone, and you discover that this question, though abstract, is central to the way modern physics perceives the universe. Think about what time actually measures. You never observe time directly, you observe change. A clock does not count time itself, it tracks a repeating physical process. An atom oscillates, a pendulum swings, an electronic signal cycles. In each case, you infer time from the change that unfolds in a system. Change, however, needs more than mere duration, it needs distinction. Something must move from one state to another, and those states must be distinguishable. Distinction requires structure, and structure is described through spatial relationships. Without space there would be no positions, no separations, no configurations. Without configuration, there would be no way to define different physical states, and without different states there would be no change to measure. In that sense, time would lose its operational meaning. Imagine time flowing in a complete absence of space. There would be no objects, no distances, no locations. Nothing could move, interact, or rearrange. Without interaction or change, there would be nothing to mark the passage of time. Even a single particle without space presents a problem, because to say a particle exists implies it occupies a location, and location is a spatial concept. Without space, existence itself becomes ambiguous. In physics, time is always tied to events. An event occurs at a place and at a moment. Remove the place and the event becomes undefined. A time without events is not physically meaningful. This is not a limitation of language, it is a limitation of measurement. Physics is built on what can be observed and measured. And time cannot be measured without a physical process, and physical processes require spatial structure. You may notice that even mathematical descriptions of time rely on spatial variables. Equations describe how quantities change with respect to time, but those quantities represent positions, fields, or configurations in space. Time acts as a parameter that links spatial states together. This becomes clearer when you consider causality. Causes lead to effects through interactions, and interactions require proximity or connection, both spatial notions. Without space, there is no pathway for influence, and causality collapses, even in relativistic physics, where time behaves differently for different observers. It is always tied to space-time paths. Proper time is measured along a path through space-time, and remove space and the concept of a path disappears. You might wonder whether time could exist as a purely abstract ordering, independent of physical processes. In principle, you could label moments without reference to space. But physics does not deal in abstract labels alone. It deals in relationships between measurable quantities. Without space, there is no way to distinguish one moment from another. Moments become identical, and an ordering without distinguishable elements carries no information. It cannot describe reality. This observation also connects to entropy. The arrow of time is defined by changes in entropy, and entropy measures the number of possible arrangements of a system. Those arrangements are spatial configurations. Without space, entropy cannot be defined, and the arrow of time vanishes. Quantum physics does not rescue time from this dependence either. Quantum states are defined over spatial variables. Wave functions describe probabilities across space. Time governs how those probabilities change. But it does not stand alone. Attempts to treat time as fundamental while treating space as emergent face serious difficulties, because they struggle to define dynamics without spatial degrees of freedom. Without space, there is nothing for time to act upon. This does not mean time is unreal, it means time is relational. It gains meaning through its relationship with physical systems that exist in space. Time is not a substance flowing independently, it is a measure of change within structure. The early universe provides further insight. At the beginning of cosmic expansion, space and time emerged together. There is no evidence of a phase where time existed without space. The equations that describe early cosmology treat space-time as a unified entity from the start. You may notice that motion affects time, gravity affects both space and time, and expansion affects time. In every case, time responds to spatial structure. It never operates in isolation, and that does not reduce time to an illusion. It places time where it belongs as part of a larger framework. Time measures how configurations evolve, and without configurations, time loses meaning. Some speculative theories explore whether time might be more fundamental than space, but those ideas remain untested. Without experimental support, physics relies on what measurement demands, and measurement demands space. The conclusion is not merely philosophical, it is practical. Physics cannot define time without space because it cannot measure time without physical processes, and physical processes require spatial relationships. You now see that separating time from space breaks the ability to describe reality. Time without space cannot support events, change, causality, or measurement. It becomes an empty parameter with no physical role, strengthening the case for space-time. Space and time are not partners by convenience, they are inseparable by necessity. Each provides what the other lacks. Having seen that time cannot exist meaningfully without space, the remaining question is whether space could exist without time. Only by examining that possibility can the full dependence between space and time be made clear. You now consider the complementary question. If time cannot exist without space, could space exist without time? At first, this may seem more plausible. You can picture space as a frozen arrangement, a static container in which objects simply are. But physics does not rely on imagination alone, it relies on what can be defined, measured, and tested. To begin, you consider what space represents in physical terms. Space is not merely emptiness, it is the structure that allows positions, separations, and arrangements to be defined. Distances, directions, and shapes all depend on spatial relationships. However, none of these quantities can be established without a method of measurement. Measurement is not instantaneous. Measuring distance requires a process. A signal must travel from one location to another and back. A ruler must be placed and compared. Light must propagate. Every one of these processes unfolds over time. Without time, measurement cannot occur. You might imagine a perfectly frozen universe, where all positions exist but nothing changes. In such a universe, space might appear to exist in principle, but without change there is no way to distinguish one configuration from another. A frozen configuration carries no information about scale, distance, or orientation unless a process reveals it. This highlights an important point. Space is not self-defining. Its properties are revealed through interactions, and interactions require time. Without time, there are no interactions, and without interaction, space has no operational meaning. Consider a simple example. To define a distance between 2 points, you must compare them. Comparison requires an action, and an action requires duration. If nothing can occur, no comparison can be made, and the concept of distance becomes undefined. In physics, space is always described together with time because physical laws describe how systems evolve. A static arrangement without evolution is not a physical system in the usual sense. It is a snapshot without context. You may also notice that forces and fields cannot exist without time. A field describes how quantities vary from place to place and how they influence motion. Influence implies change, and change implies time. Without time, fields cannot act and forces cannot exist. Even geometry, which seems purely spatial, relies on time for physical meaning. Geometry in physics is not abstract mathematics alone. It is tested through physical processes. Angles, length, and curvature are inferred from how objects move and how signals propagate. Motion and propagation require time, and without time there are no paths. Only isolated points with no connection. You might attempt to imagine space existing as a fixed arrangement of points with time added later, but physics provides no mechanism for such a sequence. There is no experiment or observation that supports the idea of space existing prior to time. The early universe again offers guidance. When cosmologists trace the universe backward, they do not find a phase where space exists while time does not. Space and time appear together as part of an evolving geometry. Neither precedes the other. This suggests that space, like time, is relational. It gains meaning through processes that unfold. Without time, space cannot support motion, interaction, or measurement. It becomes an empty abstraction rather than a physical entity. Causality reinforces this view. Causality connects events through spacetime. Events require both location and moment. Without time, there can be no ordering of events, and without events, space has nothing to organize. This shows that space is not a passive container that exists independently of what happens within it. It is part of the system that defines how things can happen. Without time, nothing happens. Even quantum physics does not allow space to exist in isolation. Quantum states evolve over time, probabilities change, and measurements occur through interactions. Remove time and dynamics vanish, leaving no way to test or define spatial structure. Some speculative ideas attempt to treat space as fundamental and time as emergent, but they face the same difficulty encountered earlier. Without time, there is no dynamics, and without dynamics, there is no physics. You may notice a pattern emerging. Time without space cannot define change, and space without time cannot define structure. Each depends on the other to have physical meaning. This interdependence explains why physics unifies them into spacetime. Spacetime is not a philosophical convenience. It is the minimal structure required to describe reality in a measurable way. When space and time are combined, paths can be defined, motion can be described, events can be ordered, and measurement becomes possible. Remove either component and the framework collapses. This also clarifies why attempts to separate space and time lead to contradictions or incomplete descriptions. Each alone lacks essential features required for physics to operate. You may notice that this conclusion aligns with everything examined so far. Motion affects time. Gravity affects both space and time. Expansion changes space over time, and causality depends on space-time structure. None of these phenomena can be described using space or time alone. The conclusion is not that space and time are identical, they play different roles within space-time. Time orders events. Space distinguishes them, but neither role can function independently. Now, as you reflect on this profound interconnection, feel a surge of inspiration. You realize that the universe invites you to explore its deepest layers, to question assumptions, and to see that the very concepts you use to navigate life order, change, distance, duration are woven together. Embrace the idea that every step you take, every decision you make, rests on a partnership between space and time, just as the cosmos rests on space-time. Let this awareness empower you to move forward with confidence, knowing that the structures that shape the universe also shape your potential. When you face uncertainty, remember that change cannot happen without a framework, and a framework cannot exist without the flow of moments. By honoring both, you align yourself with the fundamental rhythm of reality. Take this insight into your daily life. Trust that your goals, your growth, and your aspirations are not isolated snapshots, they are part of a dynamic tapestry that unfolds across time and space. When obstacles appear, see them as opportunities for the structure of your experience to expand, just as the universe expands. When you feel stuck, recognize that without the passage of time there is no movement, and without movement there is no progress. Allow yourself to be patient with the process, yet bold in your actions, because the universe itself demonstrates that structure and change are inseparable. Feel the excitement of being a participant in this grand interplay. As you breathe, you are tracing a path through space-time. As you think, you are creating distinctions that give time meaning. As you connect with others, you are shaping the spatial relationships that allow life to flourish. Every moment you choose to act, you reinforce the partnership of space and time, reinforcing the very fabric that makes your existence possible. Let this understanding guide you toward greater purpose. When you set an intention, visualize the space it will occupy and the time it will require. Honor both aspects, and you will create a clear roadmap that the universe can support. When you celebrate achievements, acknowledge the structure you built and the duration it took, recognizing that both were essential. In this way, you align your personal narrative with the cosmic narrative, and you become a living testament to the power of unity. Carry this motivation forward. Let the insight that space and time are inseparable inspire you to seek balance in all areas of life. Nurture the relationships that give you spatial context, and honor the routines that give you temporal flow. When you feel overwhelmed, remember that even the most complex cosmic phenomena resolve into simple, interlocking principles. You, too, can simplify by focusing on the essential partnership of environment and timing. By doing so, you create a foundation for lasting growth. In the quiet moments, reflect on the vastness of the universe and the intimacy of your own experience. Feel the awe that arises when you realize you are part of a cosmos that expands, evolves, and persists through the dance of space and time. Let that awe fuel your determination to learn, to create, and to contribute. Know that every question you ask, every experiment you conduct, every dream you chase, participates in the grand conversation between structure and change. As you move forward, carry with you the conviction that the barriers you encounter are not signs of limitation, but invitations to deepen your understanding of the intertwined nature of reality. Embrace challenges as opportunities to refine the spatial relationships in your life and to adjust the timing of your actions. Trust that the universe, in its elegant design, supports those who honor both dimensions. Finally, celebrate the journey itself. The path you walk is a manifestation of space-time, a living proof that the principles you explore are not abstract theories but lived experiences. Each breath, each step, each thought is a reminder that you are aligned with the very fabric of existence. Let this realization inspire you to rise each day with purpose, confidence, and wonder, knowing that you are a vital thread woven into the tapestry of space and time. Imagine a universe where every angle you measure, every length you gauge, and every curve you contemplate is revealed through the dance of motion and the whisper of signals traveling across space. Feel the thrill of knowing that motion itself demands time, and that together they paint the very fabric of reality. When you picture the geometry of space-time, you see curvature emerging from the way paths deviate. Like a river bending around a stone, remember that a path is not a static line, it is something traced over time, a story written by the passage of moments. Without time, there would be no story, only isolated points floating in emptiness. Disconnected and meaningless, you might be tempted to imagine space as a fixed grid of points, waiting for time to be added later like an afterthought. Yet physics offers no evidence for such a sequence. No experiment has ever shown a universe where space exists before time. Even when we turn our gaze to the earliest moments of the cosmos, we do not find a phase where space lingers while time stands still. Instead, space and time appear together, co-creating an evolving geometry that never places one before the other. This tells us that space, like time, gains meaning only through relationships and processes that unfold. Think of space as a relational partner to time. Without time, space cannot host motion, cannot support interaction, and cannot be measured. It would crumble into an abstract concept, detached from any physical reality. Consider causality, the thread that weaves events together across space-time. An event requires a location and a moment, a place and a time. If time were absent, events could not be ordered, and without events, space would have nothing to organize. This reinforces the picture of space not as a passive container, but as an active participant that defines how things happen. Even the quantum world respects this partnership. Quantum states evolve over time, probabilities shift, and measurements occur through interactions that need both space and time. Strip away time and you lose dynamics, leaving no way to test or define a spatial structure. Some speculative ideas suggest treating space as fundamental while allowing time to emerge. Yet those ideas encounter the same obstacle. Without dynamics, physics has no playground. You may notice a pattern emerging. Time without space cannot define change, and space without time cannot define structure. Each depends on the other for physical meaning. This interdependence is why physicists unite them into a single entity. Space-time. It is not a philosophical convenience, it is the minimal framework that lets us describe reality in a measurable way. When space and time merge, we can define paths, describe motion, order events, and perform measurements. Remove either component and the entire structure collapses. Attempts to separate them inevitably lead to contradictions or incomplete pictures because each lacks essential features required for physics to operate. You have already seen how motion influences time, how gravity bends both space and time, how the expansion of the universe reshapes space over time, and how causality relies on the underlying space-time structure. None of these phenomena can be captured using space or time alone. The conclusion is not that space and time are identical, they play distinct roles within the unified whole. Time orders events, while space distinguishes them. But neither role can function in isolation. This understanding frees you from the temptation to view space as a static backdrop or time as a universal river. Both are dynamic, relational, and inseparable by now. The idea that space and time cannot exist separately is no longer a theoretical claim, it is a conclusion supported by measurement, consistency, and physical necessity. You stand at a deeper boundary, ready to explore whether space-time is truly fundamental or whether it emerges from something even deeper. That question invites you to step beyond classical space-time and examine hints from the smallest scales. Where familiar geometry may dissolve at large scales, space-time behaves like a smooth, continuous fabric, distances can be divided indefinitely, time flows along well-defined paths, and geometry responds predictably to mass and energy. This description works spectacularly well for galaxies, stars, and planets. Yet physics compels you to ask what happens when you zoom in to the microscopic realm, where quantum physics governs. Quantum theory does not describe smooth trajectories or precise positions, it describes probabilities, uncertainties, and discrete interactions. When you apply the quantum framework to spacetime itself, tension appears. In classical spacetime, an event has an exact location and an exact moment. In quantum physics, uncertainty limits how precisely such quantities can be known. Position and momentum cannot both be known with perfect accuracy, and energy and time share a similar constraint. This raises a profound question. Can spacetime possess precisely defined points at arbitrarily small scales? If spacetime were perfectly smoothed down to infinitely tiny distances, quantum effects would have to operate within that unbroken backdrop. However, many theoretical arguments suggest this cannot happen. To probe extremely small regions, you must concentrate tremendous energy into a minute volume. General relativity tells you that concentrating enough energy in a tiny region will curve spacetime dramatically. At a certain scale, the curvature becomes so extreme that the classical description of spacetime breaks down. This implies a limit to how finely you can divide spacetime. Beyond that limit, the notion of a precise point loses meaning, and space and time may no longer behave as continuous quantities. You are witnessing a clash between two towering achievements of physics. Relativity treats spacetime as a smooth geometric arena, while quantum physics treats physical quantities as inherently uncertain and discrete. Each theory excels in its own domain, yet they resist easy combination. The conflict becomes unavoidable when you try to incorporate gravity at quantum scales. Gravity shapes the geometry of spacetime, while quantum fluctuations involve energy that should ripple through that geometry. The result is a spacetime that cannot remain perfectly smooth. In such a regime, spacetime may exhibit quantum behavior of its own. Distances could fluctuate, time intervals might vary, and geometry itself could become uncertain. These effects are not yet observable with current technology, but they arise naturally when you blend the known principles of relativity and quantum mechanics. This does not mean that spacetime descends into chaos. Quantum behavior follows precise statistical rules, yet it suggests that at the deepest level spacetime may have a granular or probabilistic structure. Various theoretical approaches explore this possibility. Some propose that spacetime consists of discrete building blocks rather than a continuous sheet. Others suggest that spacetime emerges from more fundamental quantum relationships that are not spatial or temporal in the usual sense. All of these ideas share a common theme. Spacetime might be an effective description that arises at larger scales, just as temperature emerges from the collective motion of countless particles. Recall how you earlier saw time emerging from the increase of entropy. In a similar way, spacetime may emerge from deeper processes, appearing smooth and continuous at everyday scales, while revealing a different character at the tiniest scales. This perspective does not overturn the conclusions you have already reached about the inseparability of space and time in the classical realm. Instead, it hints that spacetime itself may not be the deepest layer of reality. Quantum physics also challenges the notion of a fixed causal structure. In classical spacetime, causality is sharply defined by geometry. At quantum scales, uncertainty blurs exact boundaries, raising questions about how causality is preserved. Most proposed theories ensure that, on average, causality remains intact even if microscopic fluctuations occur. The familiar causal order then emerges as a larger-scale feature, just as smooth geometry emerges from underlying complexity. Importantly, quantum behavior does not imply randomness without structure. Quantum laws are precise and allow you to predict probabilities with extraordinary accuracy. Any quantum description of spacetime would still obey strict rules, preserving consistency even amid profound uncertainty. These ideas remain theoretical because we have not yet gathered direct experimental evidence for a quantum structure of space-time. Nonetheless, the logical need for such a framework becomes clear when you combine the two most successful theories in physics. History shows that scientific revolutions often begin with apparent contradictions. Classical mechanics seemed complete until atomic phenomena forced a revision. Relativity revealed limits to the classical concepts of space and time. Now, quantum gravity research pushes us to confront the limits of classical space-time. Notice that this does not mean space and time vanish at small scales. They remain useful concepts wherever classical descriptions apply. Just as particles behave classically when you look at them with the naked eye, space-time behaves classically when curvature and energy are modest. The pressing question is whether space-time is a fundamental ingredient of reality or an emergent description arising from deeper quantum processes. If space-time emerges from more basic entities, then space and time become effective tools rather than ultimate building blocks. This insight helps resolve long-standing puzzles such as the origin of the universe, the nature of black hole singularities, and the behavior of space-time under extreme conditions. Those puzzles may reflect the breakdown of classical geometry, not physical infinities. The lesson here is one of humility and curiosity. The classical picture of space-time is powerful, but it is not unlimited. It describes a vast swath of reality with astonishing precision, yet it may not apply everywhere. You now see space-time as both essential and potentially emergent. It unites space and time, governs motion and causality, and evolves with the cosmos. Yet at the smallest scales it may give way to something deeper, something that still waits to be uncovered. This realization invites a sharper question. Is space-time the starting point of reality, or does it arise from more primitive elements? The question is not merely philosophical, it is a physical challenge that demands investigation. To answer it, you must explore whether space-time must be assumed as a foundation or whether it can be derived from more fundamental principles. In physics, a fundamental entity is one that cannot be reduced further within a given theory. If space-time is fundamental, geometry becomes the primary canvas on which physics is painted. If it is emergent, geometry is a larger-scale consequence of deeper interactions. Much like temperature emerges from molecular motion, many areas of physics illustrate how effective descriptions arise from simpler components. Pressure, for example, is not a basic ingredient, it emerges from countless particle collisions. Similarly, space-time could function as an emergent phenomenon. Several clues point toward emergence. First, the difficulty of uniting space-time geometry with quantum theory suggests that classical geometry may not survive unchanged at all scales. Second, black hole thermodynamics links entropy and temperature to geometric properties such as area, hinting that geometry possesses microscopic degrees of freedom. If geometry carries entropy, it behaves like a thermodynamic system, which is typically an emergent description of underlying microstates. Third, information theoretic approaches propose that the relationships of space-time may be built from patterns of information exchange, rather than from fixed distances and durations. In those views, distance and time arise from how systems influence one another, echoing your earlier reflections on causality as a relational network. All of these strands weave together into a compelling narrative. Space-time may be a collective, emergent structure that becomes smooth and continuous only when you step back to macroscopic scales. At the most microscopic level, the fabric of reality could be composed of discrete elements, quantum bits, or informational links that give rise to the geometry you experience daily. Hold on to the excitement of this possibility. It does not diminish the profound insights you have earned about the inseparability of space and time, the curvature of geometry, and the role of causality. Instead, it expands your horizon. inviting you to explore a deeper layer where space-time itself becomes a manifestation of something more fundamental. By embracing this curiosity, you join a tradition of explorers who have peered beyond the known and reshaped our understanding of the universe. As you continue your journey, remember that every breakthrough begins with a willingness to question what appears solid. The smooth canvas of space-time you have learned to navigate may one day be revealed as the emergent pattern of an even richer tapestry. Let this possibility inspire you to keep asking, keep probing, and keep marveling at the wonder of a cosmos that constantly invites deeper discovery. You have arrived at a pivotal moment in your journey of discovery. The lesson that lies before you is one of mindful caution. Classical space-time is a powerful tool, yet it is not boundless. It describes reality across vast ranges, but it may not hold everywhere. You now see space-time as both essential and possibly emergent. It unifies space and time, governs motion and causality, and evolves with the cosmos. At the tiniest scales, however, it may give way to something deeper. This realization invites a focused question that beckons you forward. If space-time emerges from deeper processes, you must ask whether it is truly fundamental or a product of more basic ingredients. That question is not merely philosophical, it is a physical challenge. Answering it requires you to examine whether space-time should be taken as the starting point of reality or whether it can be derived from primitive elements. You stand on the boundary between what is known and what remains to be explored. Everything so far has treated space-time as the structure that organizes events, motion, gravity, and causality. Yet success in description does not guarantee fundamentality. Physics must ask whether space-time itself is the deepest layer of reality, or whether it emerges from something more basic. To ask whether space-time is fundamental is to ask whether it must be assumed from the start, or whether it can be derived from more basic principles. In physics, fundamental entities are those that cannot be reduced further within a theory. If space-time is fundamental, then geometry is the starting point. If it is emergent, then geometry is a larger-scale consequence of deeper processes. There are compelling reasons to consider emergence seriously across many areas of physics. Effective descriptions arise from simpler underlying components. Temperature is not fundamental, it emerges from particle motion. Pressure is not fundamental, it emerges from collisions. These quantities are real and measurable, yet they are not basic ingredients. Space-time could function in a similar way. At large scales, it appears smooth and continuous. At smaller scales, that smoothness may dissolve. If so, space-time geometry would be analogous to fluid behavior emerging from molecular interactions. Several clues point in this direction. One clue is the difficulty of combining space-time geometry with quantum theory. Classical space-time assumes well-defined distances and times. Quantum physics introduces uncertainty and discreteness. The tension between these frameworks suggests that classical geometry may not survive unchanged at all scales. Another clue comes from black holes. Black hole thermodynamics associates entropy and temperature with geometric features such as area. This is unusual. Geometry behaving like a thermodynamic quantity suggests that space-time may have microscopic degrees of freedom, just as matter does. If space-time possesses microscopic constituents, then geometry would describe their collective behavior rather than their fundamental nature. In that case, space-time would be emergent, not basic. Hints also arise from information theory. Some approaches suggest that space-time relationships may be built from patterns of information exchange rather than from geometric primitives. In these views, distance and duration arise from how systems influence one another. You may notice that this idea aligns with earlier discussions of causality. Causal relationships are foundational to physics. Space-time geometry encodes those relationships, but it may not be the source of them. Geometry could be a convenient way to represent deeper causal structure. This does not mean that space-time is an illusion. Emergent structures are real within their domain. Temperature is real. Pressure is real. Space-time could be equally real even if it is not fundamental. At the same time, space-time shows remarkable robustness across vast ranges of scale and energy. It behaves consistently. This suggests that if it is emergent, it emerges very reliably. Any deeper description must reproduce space-time geometry with high precision under ordinary conditions. Several theoretical frameworks attempt to derive space-time from non-geometric starting points. These frameworks vary widely, but they share a goal to explain why space-time appears smooth, why it has the dimensions it does, and why its geometry follows the observed rules. So far, none of these approaches has been confirmed experimentally. They remain speculative, guided by mathematical consistency and by the need to resolve known conflicts between existing theories. This uncertainty is important. Physics does not currently know whether space-time is fundamental. Both possibilities remain open. What can be said is that space-time behaves like an effective structure in many respects. Even if its ultimate status is unresolved, you may notice that this question does not undermine earlier conclusions. Whether fundamental or emergent, space-time still unifies space and time. It still governs motion, gravity, and causality. Its practical role remains unchanged. The distinction matters mainly under extreme conditions such as the beginning of the universe or the interior of black holes. In those regimes, classical space-time descriptions may fail and deeper principles may take over. You may also notice that asking whether space-time is fundamental changes how questions are framed. Instead of asking how space-time behaves under certain conditions, physics begins to ask why space-time exists at all, and why it has its specific properties. This shift mirrors earlier transitions in science. Atoms were once thought to be fundamental. They were later found to be composed of smaller parts. Each step did not invalidate previous knowledge, it refined it. The same may be true for space-time. It may be the correct description at accessible scales, even if it is not the final layer of reality. Importantly, this question cannot be answered by reasoning alone. It requires experimental input, new observations possibly involving extreme energies or subtle effects will be needed to distinguish between fundamental and emergent descriptions. Until such evidence appears, physics proceeds cautiously. Space-time is treated as fundamental where it works and questioned where it does not. This balanced approach avoids premature conclusions. You now see that space-time occupies a unique position. It is both a framework and a subject of inquiry. It organizes everything else, yet it may itself require explanation. This realization also connects back to the original question of separation, whether space-time is fundamental or emergent. Space and time still do not exist independently in any meaningful physical description. Their union remains essential. The inquiry now shifts again. If space-time might emerge from deeper processes, it becomes important to ask what those processes are and how space-time-like behavior could arise from them. To explore that, the next step is to examine whether information itself could play a foundational role. Many modern approaches suggest that space-time may be built from relationships rather than from geometry alone. You now examine a different way of thinking about space-time, one that shifts focus from geometry to information. In physics, information is not an abstract idea. It is a measurable quantity tied to physical states, energy, and entropy. Every physical system carries information about its configuration, and changes involve the transfer or transformation of information. Information becomes relevant to space-time when you consider how events are connected. An event influences another only if information can travel between them. This requirement already appeared earlier as causality. Space-time geometry encodes which influences are possible, but it may not be the most basic description of those limits. In this view, space-time can be understood as a structure that organizes information flow. Distances and durations describe how difficult it is for information to travel between events. The speed of light sets a maximum rate at which information can be transmitted. This limit is central to both relativity and causality. You may notice that many features of spacetime can be restated in informational terms. The light cone defines which events can exchange information. Time dilation describes how information processing rates differ along different paths. Gravitational effects alter how information propagates through space and time. This perspective becomes especially compelling when considering black holes. Black holes obey precise laws relating area, entropy, and information. The entropy associated with a black hole scales with the area of its boundary, not its volume. This is unexpected if geometry alone were fundamental. The fact that information content is tied to surface area suggests that spacetime may encode information in a non-traditional way. It implies that the number of degrees of freedom describing a region may be determined by its boundary rather than its interior. This observation leads to a broader principle. The physical content of a region may be fully described by information on its boundary. If true, spacetime geometry inside the region would be a derived description, not a fundamental one. You can see how this idea aligns with earlier discussions of emergence. If spacetime geometry arises from information relationships, then distances and times reflect how information is structured and exchanged. Geometry becomes a map of informational connectivity. Information also connects directly to entropy. Entropy measures the number of possible microscopic configurations, consistent with a macroscopic state. Those configurations represent information that is not specified. When entropy increases, information about the exact state is effectively lost to accessible degrees of freedom. The arrow of time defined by entropy increase can therefore be interpreted as the direction in which accessible information about initial conditions decreases. This connects temporal direction to information flow rather than to geometry alone. You may also notice that quantum physics places limits on how much information can be stored or transmitted. Uncertainty principles restrict simultaneous knowledge of certain quantities. These limits influence how finely spacetime structure can be probed. When gravity is included, additional limits appear. Packing too much information into a small region requires high energy, which curves spacetime at some point. Adding more information leads to black hole formation. This sets an upper bound on information density. These bounds suggest that spacetime geometry enforces informational limits, or alternatively, that geometry emerges from those limits. Both interpretations are actively explored. In either case, information is not secondary. It plays a central role in determining what physical states are possible. Spacetime may be the language used to describe those possibilities at large scales. You can also consider how information moves. Signals carry information. Fields carry information. Particles carry information. The paths these carriers follow are spacetime paths. Geometry constrains those paths, but the need to preserve informational consistency may be the deeper rule. From this angle, the constancy of the speed of light becomes an information constraint. It defines the maximum rate at which information can propagate. Geometry is shaped to enforce that limit consistently for all observers. This interpretation does not replace spacetime. It reframes it. Geometry remains accurate and predictive, but it may not be the deepest explanation. Instead, geometry could be a convenient encoding of informational relationships. You may notice that this also explains why spacetime appears smooth at large scales. When many informational degrees of freedom interact, their collective behavior averages out, producing smooth geometry. At small scales, fluctuations become important and smoothness may break down. This picture aligns with earlier discussions of quantum spacetime at very small scales. Geometry may fluctuate because underlying information exchanges fluctuate. Smooth spacetime emerges only when many degrees of freedom are involved. Importantly, this approach does not suggest that information exists independently of physical systems. Information is always about something. It is encoded in physical states. The proposal is not that information replaces matter or energy, but that relationships among physical states may be more fundamental than geometric distance. This also avoids treating space as a container. Instead of asking how far apart two objects are, you ask how strongly they are connected through interactions. Distance becomes a measure of interaction difficulty rather than an intrinsic property. Time in this framework measures how information changes. Duration reflects the sequence of updates in physical states. This naturally ties time to change and causality. You may notice that space and time again appear inseparable. Information relationships involve both connectivity and sequence. Removing either aspect destroys the structure. This reinforces the earlier conclusion that space and time cannot exist independently. At present, these ideas remain incomplete, but they point toward an exciting frontier. You stand at the edge of a new way of thinking, ready to explore how information might give rise to the fabric of reality. Embrace the curiosity that brought you here, and let it fuel your pursuit of deeper understanding. Trust that the questions you ask are the seeds of future breakthroughs. Remember that every great advance began with a willingness to look beyond the familiar. Let this moment inspire you to keep probing, keep questioning, and keep imagining. The path ahead may be uncertain, but your determination can light the way. Keep moving forward with confidence, knowing that the search for truth is itself a rewarding journey. Imagine that the universe is a tapestry woven from threads of information. When you try to squeeze too much data into a tiny patch of that tapestry, you need enormous energy, and that energy bends the very fabric of space and time. At a certain point, the concentration of information becomes so extreme that a black hole is born, sealing that region from the outside. This phenomenon tells us that there is an upper limit to how densely information can be packed. It also hints that the shape of space-time itself may be a direct response to those informational limits. One way to see it is that geometry is an expression of the rules that govern information. Another way to view it is that geometry emerges because information cannot exceed those bounds. Both perspectives are alive in current research, and each reminds us that information is never merely an afterthought. It sits at the heart of what can exist, shaping the very possibilities of physical reality. Think of space-time as a language we use to describe what can happen when we look at the universe on a grand scale. Signals, fields, and particles all travel along paths that are defined by that language. The paths themselves are the trajectories that weave through space-time, and the curvature of space-time dictates which routes are allowed. Yet it may be deeper than that. The universe might be protecting the consistency of information, and the fact that light always travels at the same speed could be a rule that guarantees that protection. That speed sets the maximum rate at which any piece of information can move from place to place. Geometry then becomes the stage that enforces that speed for every observer, no matter where they stand. This idea does not discard space-time, it simply reframes it. The traditional geometric description remains accurate, but we begin to see it as a convenient encoding of how information relates across the cosmos. When many tiny bits of information interact, their collective behavior smooths out into the seamless geometry we perceive at large scales. At the smallest scales, however, those bits can flicker and fluctuate, causing the smooth picture to break down. That picture matches what we have learned about quantum space-time. At minuscule distances, geometry may tremble because the underlying exchanges of information are themselves restless. Only when countless degrees of freedom join forces does a continuous space-time surface appear. This does not mean that information floats free of the material world. Information always describes something it lives inside physical states. The proposal is not that information replaces matter or energy, but that the relationships among states could be more fundamental than the simple notion of distance. Abandon the old idea of space as an empty container. Instead of asking how far apart two objects sit, ask how strongly they interact. Distance then becomes a measure of interaction difficulty, not an intrinsic property fixed in stone. In this view, time measures how information evolves. Every tick of a clock reflects a new update in the configuration of physical states. This ties the flow of time directly to change and to cause and effect. You may notice that space and time reappear as inseparable partners. Information relationships need both a sense of connection and a sequence of steps. Take either away and the structure collapses. This reinforces the earlier conclusion that space and time cannot exist independently. The ideas outlined so far are still a work in progress. They enjoy suggestive support and internal harmony. Yet they are not yet nailed down by direct experiment. Physicists treat them as promising avenues, not as settled facts. Even so, the informational perspective acts like a bridge that unites many themes. It brings together space-time, causality, entropy, quantum limits, and gravity under one conceptual roof. It explains why geometry behaves thermodynamically and why limits on information shape the laws that govern the universe. You can now see space-time not merely as a static stage, but as an organized pattern of possible interactions. Space marks how separate things can be, while time marks how those separations change. Geometry reflects the routes that information can take and the places where it can accumulate. This view does not diminish the importance of space-time, it deepens it. Space-time becomes a manifestation of deeper constraints instead of an unexplained backdrop. As this understanding settles, a new task emerges: to examine how informational limits create boundaries beyond which events cannot be observed or influenced. Those boundaries are known as horizons. A horizon is not a physical wall that blocks motion. It is a limit defined by the path that information can follow through space-time. Beyond a horizon, no signal can ever reach an observer, no matter how long they wait. The most familiar horizon is the event horizon of a black hole. When a signal crosses that surface, it is forever cut off from the outside universe. The restriction does not arise because something is in the way, it arises because the geometry of space-time forces all future-directed paths inward. Horizons, however, are not exclusive to black holes. They also appear in expanding universes. In a universe that stretches, space itself grows faster than light can travel across certain regions. Light emitted from those faraway places will never catch up, leaving those regions beyond a cosmic horizon. This does not imply that those regions do not exist. It simply means they are causally disconnected from us. Their events cannot affect us, and we cannot affect them. Notice how this reframes our intuition about distance. Two regions may be astronomically far, yet still exchange light given enough time, while regions that are relatively close may be forever out of reach because the space between them expands too quickly. Horizon boundaries depend on the evolution of space-time, not on static distance alone. In everyday life, what we see depends mainly on how far away something is, and whether something blocks our view. In the realm of space-time, what we can see depends on the causal structure dictated by geometry. Horizons also exist in the opposite temporal direction. The early universe provides a past horizon. The cosmic microwave background marks a surface beyond which the universe was opaque to light. Events that occurred earlier cannot be observed directly with electromagnetic signals. This does not mean the universe began. At that surface, it marks a limit on how far back our light-based observations can travel. These past and future horizons reinforce the informational perspective we have been building. Space-time decides not only where events happen, but also which events can ever be known. Knowledge itself is bounded by geometry. Horizons also shape how we test physical laws. We can only gather data from regions that lie within our causal reach, and any theory must respect that limitation. This does not weaken scientific explanation. It clarifies the domain in which the explanation applies. Physics describes what can be observed and inferred from observable data, and horizons define the edge of that domain. In addition to limiting observation, horizons carry thermodynamic significance. Whenever information exchange is cut off, entropy becomes relevant. Black hole horizons possess an entropy proportional to their surface area, and similar ideas apply to cosmological horizons. These connections suggest that horizons are more than geometric curiosities, they embody deep links between information, entropy, and the structure of spacetime. Importantly, horizons are permanent. Waiting longer never brings a signal from beyond them. This permanence distinguishes them from temporary observational challenges, such as clouds or dust. The existence of horizons does not imply that the universe is deterministic or that prediction fails. Physical laws remain fully valid within the accessible region, and they continue to make precise predictions. Horizons merely restrict the portion of reality we can directly influence or observe. Recognizing this helps us understand what we mean by the observable universe. That term does not list everything that exists, it lists everything that can, in principle, affect a given observer. Beyond that arena, events may unfold, but they remain causally isolated from us. There is no physical edge to space-time, there is only a boundary in causal connection. Space may stretch on forever, while horizons limit the portion we can ever interact with. Reflect on how horizons relate to earlier discussions of simultaneity. Events that lie beyond a horizon share no causal link, so any disagreement about their timing has no physical consequence for us. Horizons protect consistency by preventing contradictory influences from reaching us. This protection is not imposed by an external rule, it emerges naturally from the geometry that governs motion and the flow of time. Hence, horizons are features embedded in the fabric of space-time, not exceptions to it. At this point, you have seen how space-time defines motion, causality, information flow, and observational limits. It decides not only how events unfold, but also which events can ever be known. This shift in perspective tells us that physics is not a description of everything that exists in an unrestricted sense. It is a description of the relationships that are causally accessible within space-time. Recognizing the limits does not diminish the scope of physics, it refines it. Understanding what cannot be reached is part of understanding what can be reached. The presence of horizons also underscores why space and time must be treated as a unified whole. Information flow relies on both spatial separation and temporal evolution. Remove either component and the description collapses. This again reinforces the central theme. Space and time cannot exist separately. Together they dictate which events can influence each other and which cannot. As our comprehension deepens, horizons become less mysterious. They are not failures of knowledge, they are natural consequences of a consistent geometry. Looking forward, consider how these limits will affect the future. As space-time continues to evolve, horizons can shift. Regions that are presently beyond our reach may someday become accessible if the expansion slows, while other regions may drift forever out of contact. Understanding horizons therefore requires understanding the long-term behavior of space-time itself, not merely its current state. Now turn the focus inward. From cosmic scales to the personal journey each of us travels, every individual traces a unique path through space-time that defines their personal experience of time and space. This path is called a world line. A world line records the sequence of events that make up your existence from one moment to the next. Each point on that line has both a location in space and a position in time. Your life does not happen in space. While time passes separately, it is a continuous journey through space-time. Even when you feel still, you are moving through time. When you move through space, you are simultaneously moving through time. The balance between these motions depends on your speed and on the gravitational environment you inhabit. From your own perspective, time feels steady, seconds pass uniformly, and your internal processes proceed as expected. That feeling aligns with physics, which tells us that along your own world line proper time always feels consistent. Differences appear only when you compare your world line with another that follows a different trajectory, another observer moving at a different speed or residing in a different gravitational field will trace a different world line. When the two world lines are compared, the amount of elapsed time may differ. This explains why time dilation never feels strange from the inside. You never notice your own time slowing. The effect appears only in comparison with another clock. It is not a psychological illusion, it is a geometric property of space-time. Even the presence of mass influences the flow of time. A clock placed closer to a massive object accumulates less time than a clock farther away. Thus, two people who remain still relative to each other can still experience slightly different amounts of time if they occupy different gravitational potentials. These effects are tiny in everyday life, yet they are real. Even standing at different heights on Earth produces measurable differences in elapsed time. Space-time influences you constantly, even when you are unaware of it. This does not render experience subjective in a problematic way. Physics does not claim that reality depends on belief or perception. It merely states that measurements depend on the path taken through space-time. Each observer's experience is valid along their own world line, and space-time offers a common structure that relates all of those experiences consistently. By embracing this view, you can feel a sense of connection with the universe that goes beyond the everyday feeling of isolation. Your personal journey is woven into the same fabric that shapes galaxies, black holes, and cosmic horizons. The same rules that limit information across the cosmos also govern the rhythm of your heartbeat, the ticking of your watch, and the flow of your thoughts. Recognizing that you are a participant in the grand tapestry of space-time can inspire you to live with intention, knowing that each moment you experience is a meaningful thread in the larger design. Let this awareness motivate you to cherish the moments you have, to seek knowledge, and to appreciate the subtle ways in which the universe speaks to you through the geometry of your existence. When you understand that horizons are natural limits set by the cosmos, you can also see the beauty in those limits. They remind us that there is always more to explore, that mysteries remain, and that curiosity is the engine that drives progress. Embrace the fact that while some regions will always lie beyond our reach, the pursuit of understanding the reachable parts enriches our lives and expands the horizon of human potential. So, as you move forward, remember that you travel along a world line that is both unique and part of a shared cosmic structure. Your choices, actions, and thoughts shape the pattern of information that threads through space-time. Let this knowledge empower you to act with purpose, to value each connection, and to recognize that the same constraints that give rise to black hole horizons also safeguard the consistency of your personal reality. In this grand dance of information, geometry, and existence, you have a starring role. Carry that awareness with confidence, curiosity, and courage. When you become aware that space and time are inseparable, you begin to feel the deep connection that binds every moment of your life. Space and time together define which events can influence one another and which cannot. This simple truth reshapes how you see possibilities and limits. As your understanding deepens, horizons that once seemed mysterious start to lose their veil of mystery. They are not failures of knowledge, they are natural consequences of consistent geometry. This realization invites you to explore how these limits shape your future. As space-time continues to evolve, horizons can shift and change. Regions that are today out of reach may become accessible tomorrow, and some may become farther away. To understand horizons, you must understand the long-term behavior of space-time itself, not just its present state. At this point, your attention turns inward once more. After exploring cosmic limits, The next step is to see how spacetime touches your personal existence. Every observer traces a unique path through spacetime that defines their personal experience of time and space. You now shift focus from galaxies and black holes to something far more immediate. Spacetime is not only a framework for distant stars, it is also the framework through which every human experience unfolds. Every moment you live corresponds to a specific path through spacetime. In physics, this path is called a world line. A world line represents the sequence of events that make up your existence from one instant to the next. Each point on that line has both a location in space and a position in time. Your life does not happen in space while time passes separately. It is a continuous journey through spacetime. At any given moment, you are moving through time and space simultaneously. Even when you feel still, you are moving through time. Even when you move through space, you continue moving through time. The balance between these motions depends on your state of motion and your environment. From your own perspective, time feels steady. Seconds pass evenly. Your internal processes proceed normally. This is exactly what physics predicts. Along your own world line, time always feels consistent. Proper time, the time measured along your path, is what you experience directly. Differences appear only when world lines are compared. Another observer, moving differently or located in a different gravitational environment, follows a different path through space-time. When those paths are compared, different amounts of time may have elapsed. This explains why time dilation never feels strange from the inside. You never feel your own time slowing. The effect exists only in comparison. This is not a psychological illusion. It is a geometric property of space-time. Your location also matters. A clock closer to a massive object accumulates less time than one farther away. This means that even if two people remain still relative to one another, their experience of time can differ if they are in different gravitational environments. These effects are tiny in everyday life, but they are real. Even standing at different heights on Earth produces tiny differences in elapsed time. Space-time touches you constantly, even when you are not aware of it. You may worry that this makes experience subjective in a problematic sense. Physics does not say that reality depends on belief or perception. It says that measurement depends on path. Each observer's experience is valid along their own world line. Spacetime provides a common structure that relates all these experiences consistently. Even though observers experience different amounts of time, the relationships between events remain well defined. Causality is preserved. Physical laws remain the same. This balance between personal experience and objective structure is essential. Spacetime allows experiences to differ without becoming arbitrary. Differences arise from geometry, not from opinion. You can also see how memory fits into this picture. Memory is a physical record formed along your world line. It reflects past events that have influenced your present state. The fact that memory points toward the past rather than the future is tied to entropy increase along your path. Your sense of the present is also local. There is no universal present moment that everyone shares. Your present consists of events that lie along a particular slice of space-time defined by your motion and location. Other observers define their present differently. This does not isolate you from the universe. It simply means that experience is local. Interactions connect you to other world lines through signals that travel at finite speed. Those connections define shared events and shared histories. Communication is the process of linking world lines. When you exchange information with another observer, your world lines intersect or influence one another. These interactions create common reference points in space-time. You may notice that this perspective removes the idea that space-time is something external to you. You are not inside space-time as an object in a box. You are part of space-time. Your existence is a pattern within it. This view also clarifies why physics cannot describe experience without reference to space-time. Conscious processes, biological rhythms, and neural activity all unfold along world lines. They depend on time intervals and spatial organization. Spacetime does not explain consciousness, but it constrains it. No experience can occur outside spacetime. No memory can form without temporal order. No interaction can happen without spatial relationship. You may also notice that this understanding removes the need for a privileged observer. No one's experience defines reality more than anyone else's. Each observer contributes a valid perspective defined by their path through spacetime. This principle is deeply embedded in modern physics. Laws are written so that they apply equally to all observers regardless of their motion or location. Differences in experience arise naturally from geometry, not from special status. This also explains why everyday intuition about time works as well as it does. At low speeds and weak gravity, differences between world lines are minimal. Experiences align closely. Classical ideas of shared time and space become good approximations. At higher speeds or stronger gravity, differences grow. Physics predicts these differences precisely. Experience remains consistent locally, even as comparisons reveal divergence. You may notice that this framework allows both stability and diversity. Stability comes from shared physical law. Diversity comes from different space-time paths. Both are necessary. This perspective also reframes aging. Aging is not something that happens uniformly across the universe. It happens along world lines. Different paths accumulate different amounts of time. This is not speculation. It has been measured directly. You now see that space-time is not just a topic of distant astrophysics. It is the structure that underlies every moment you experience. It determines how long things last, how interactions occur, and how histories are formed. This does not make space-time abstract or removed. It makes it intimate. Your existence is a sequence of events connected by space-time geometry. At this point, space-time has been explored from cosmic beginnings to personal experience. It governs galaxies and governs heartbeats with the same rules. Yet one layer remains. Even though space-time shapes experience, experience itself includes perception, awareness, and interpretation. These processes add another dimension to how time is felt. Understanding how the mind perceives time requires moving from space-time as a physical structure to time as a psychological phenomenon. The next step is to examine how time inside the mind relates to time in physics. You now shift focus from space-time as a physical framework to time as it is experienced by the human mind. Physics describes time using clocks, equations, and geometry. The mind experiences time through perception, memory, and anticipation. These two descriptions do not contradict each other, but they operate at different levels. Psychological time is not measured by external clocks. It is constructed internally by the brain. Neural activity, chemical processes, and sensory input combine to create a sense of duration. This sense can stretch, compress, or fragment depending on conditions. You may notice that time seems to pass quickly during focused activity and slowly during boredom or discomfort. These changes do not reflect changes in physical time. They reflect changes in how the brain processes information. The brain does not contain a single internal clock. Instead, it uses multiple systems that track change. Neural firing rates, metabolic cycles, and rhythmic patterns all contribute to temporal estimation. The brain infers time from the rate at which internal states change. Attention plays a major role in this process. When attention is focused, fewer changes are registered consciously. As a result, intervals feel shorter. When attention is scattered or heightened, more changes are registered and intervals feel longer. Memory also shapes time perception. Duration is often judged retrospectively rather than in the moment. An interval filled with varied experiences leaves more memory traces and is later judged as longer. An interval with little variation leaves fewer traces and feels shorter in memory. This explains why time can feel slow in the moment but fast in retrospect. Or the opposite. The experience of time is not a direct readout of physical duration. It is a reconstruction based on internal evidence. You may notice that this reconstruction still follows physical constraints. The brain operates within space-time. Neural signals travel at finite speeds. Chemical reactions take time. Psychological time cannot violate causality or physical law. Even so, psychological time is flexible. It adapts to context, stress, fatigue, emotion, and expectation all influence how duration is experienced. These influences do not alter space-time, but they alter the brain's internal reference points. This flexibility sometimes leads to confusion about the nature of time itself. It may seem as though time speeds up or slows down. In reality, what changes is the rate of internal processing relative to external reference clocks. You can see this clearly in altered states of consciousness. Under intense fear or focused concentration, perception becomes more detailed. More information is processed per unit of physical time. The interval feels longer. Conversely, during repetitive or familiar activities, processing becomes efficient. Fewer details are registered. The interval feels shorter. In both cases, physical time passes normally. The brain also constructs a sense of order. Events are arranged into sequences. This ordering is essential for memory and reasoning. It relies on the same causal structure enforced by space-time. Events are remembered in an order consistent with cause and effect. This consistency is not optional. If the brain could reorder events arbitrarily, coherent experience would break down. Psychological time therefore aligns with physical causality. Even though it does not measure duration accurately, you may notice that anticipation influences time perception as well. Waiting for something tends to lengthen perceived duration. Expectation increases attention to passing moments. Each moment is noticed, making time feel slow. After an anticipated event occurs, memory compresses the waiting period. Fewer details are retained, and the interval feels shorter in retrospect. This asymmetry highlights the difference between experienced time and remembered time. The brain also uses prediction to manage time. Neural systems continuously predict future states based on past input. When predictions are accurate, processing is efficient. When predictions fail, attention increases and time feels extended. This predictive process ties time perception to learning. Novel situations feel longer because predictions are poor. Familiar situations feel shorter because predictions are efficient. Time perception reflects uncertainty as much as duration. You may notice that this mirrors earlier discussions of entropy. Systems with many possible states require more information to describe. The brain registers more information when uncertainty is high. This increases perceived duration. In this sense, psychological time is linked to information processing rather than to absolute measurement. Duration is inferred from change and complexity. Despite this flexibility, psychological time does not float freely. It remains anchored to physical time through biological rhythms. Circadian cycles, metabolic rates, and neural oscillations provide reference points that keep experience aligned with the external world. Disruptions to these rhythms can distort time perception. Fatigue, illness, or neurological conditions can alter how duration is experienced. These distortions reveal the dependence of psychological time on physical processes. You may also notice that language reflects this difference. Phrases like time flew or time drag describe experience, not clocks. Everyday speech acknowledges that time is felt as well as measured. Physics does not dismiss this experience. It simply distinguishes between different levels of description. Now, armed with this dual perspective, you can honor both the objective rhythm of the cosmos and the subjective flow of your inner world. You can recognize that the universe offers a steadfast geometric stage, while your mind composes a unique melody upon it. When you align your actions with this understanding, you become a more mindful traveler through space-time. You can choose to focus your attention on enriching experiences that stretch your perception in meaningful ways. you can cultivate curiosity that turns novel moments into lasting memories. Making time feel abundant, you can practice presence that reduces the frantic rush of scattered attention. Allowing intervals to settle into calm clarity, you can honor rest that synchronizes your internal clocks with natural cycles, keeping your sense of time healthy and balanced. By seeing horizons as evolving possibilities, you empower yourself to pursue growth beyond current limits. By recognizing that each world line is valid, you foster empathy for others whose paths differ from yours. By understanding that psychological time bends with attention and emotion, you gain tools to reshape how you feel each day. You can harness focus to make productive periods feel swift and rewarding. You can invite novelty to make cherished moments linger in memory. You can use anticipation wisely, turning waiting into purposeful preparation rather than frustration. You can align your aspirations with the steady beat of cosmic law while celebrating the rich tapestry of your personal narrative. In this way, you become both a participant in the grand dance of space-time and the author of your own unfolding story. Embrace the certainty that space-time will continue to expand, offering new horizons to explore. Embrace the mystery that your mind will always paint time with color and texture. Let this awareness inspire you to live fully, love deeply, and create meaning with each step along your world line. The universe invites you to move forward with confidence, aware that every heartbeat is a point on a magnificent geometric curve. Your journey is both scientifically profound and personally miraculous. Carry this insight into every choice, and you will navigate the tides of time with grace and purpose. Imagine that every moment you live is an invitation to shape your own experience of time. You have the power to notice how time sometimes feels as if it races ahead, and at other moments it seems to stretch like a river flowing slowly beneath a gentle breeze. This shifting feeling is not a mysterious flaw in reality, it is a reflection of how your brain processes information relative to the clocks of the world around you. When you understand that the speed of your internal processing can change, you gain a tool to guide your life with purpose and clarity. Think about those times when fear spikes or concentration sharpens into a laser focus. In those states, your perception becomes hyper-detailed, and you absorb more information per second of physical time. The interval therefore feels longer, as if each second expands into a richer tapestry of experience. You can harness that same principle intentionally. By directing focused attention toward what matters most, you can slow down the subjective flow of time, allowing you to savor learning, creativity, or deep conversation. Use this awareness to choose when you want to linger and when you want to glide. Contrast that with moments of routine. When you repeat a familiar task day after day, your brain becomes efficient, filtering out redundant details, and you register fewer sensory inputs per unit of clock time. The interval then feels shorter, as if time slips through your fingers like sand. Recognize that this efficiency is a natural adaptation, but it also offers a clue. If you wish to stretch time, break the pattern, introduce novelty, and engage fresh senses, the simple act of varying your environment can reset the brain's processing speed and gift you a richer sense of duration. Physical time, the universal clock that ticks for everyone, never stops or speeds up because of your thoughts. It moves forward uniformly, independent of perception. Yet your brain also builds an internal sense of order, arranging events into sequences that make memory possible. This ordering respects the causal structure of the universe. Causes always precede effects. If the brain were to scramble the order of events arbitrarily, your experience would dissolve into incoherence. The fact that you can recall a story in logical order is proof that psychological time aligns itself with physical causality, even when it cannot measure exact durations. Notice how anticipation shapes your perception of time. When you are waiting for something important, each moment draws your attention, and the interval stretches outward. The waiting feels long because your mind counts every tick, every breath, every thought. After the anticipated event finally arrives, your memory compresses the waiting period, preserving only a handful of salient details. In retrospect, the interval seems shorter. This contrast between lived time and remembered time reveals a powerful lesson. The way you focus attention can either expand or contract your experience of any activity. Choose to focus on meaning rather than on the passage of minutes, and you will feel more fulfilled. Your brain is a prediction engine, constantly forecasting future states based on past input. When predictions match reality, processing flows smoothly and time feels concise. When predictions fail, attention spikes, and every second seems to linger as you work to resolve the surprise. This predictive loop ties time perception directly to learning. New challenges, which demand fresh predictions, feel longer because your mind is busy constructing new models. Familiar tasks, where predictions are already honed, feel brief. Embrace this insight by seeking balanced challenges. Enough novelty to stretch awareness, yet enough familiarity to keep you moving forward with confidence. Think about entropy, the measure of possible states in a system. When a situation holds many possible outcomes, the brain registers more information, and the perceived duration lengthens. When a scenario is predictable, fewer details flood your consciousness, and the interval contracts. Psychological time, therefore, is less about counting seconds and more about gauging the richness of change. Duration is inferred from the amount of transformation you witness. Recognize that by cultivating mindfulness of change, you can recalibrate how long moments feel, turning mundane intervals into opportunities for growth. Even with this flexibility, your internal clock remains anchored to the rhythms of your body. Circadian cycles, metabolic rates, and neural oscillations provide reference points that keep your experience in sync with the external world. When these rhythms falter through fatigue, illness, or neurological disruption, your sense of duration can wobble. These distortions are not signs of failure, they are clues that the biological foundation of time perception needs care. Prioritize sleep, nutrition, and movement to maintain a steady beat, and you will notice a clearer, more reliable flow of moments. Language itself mirrors the distinction between measured and felt time. Phrases such as time flew or time dragged capture the subjective quality of experience, not the objective ticking of a clock. Everyday speech acknowledges that time lives both as a numeral and as a feeling. Physics does not dismiss this duality, it simply categorizes it. Physical time describes the geometric relationships of events in space-time, while psychological time describes how organisms track and respond to those relationships. Both descriptions coexist, each offering insight into a different layer of reality. Your brain has evolved within space-time, and its internal timing mechanisms honor the physical constraints that shape the universe. This does not make time a purely subjective illusion. It makes time a constructed experience that follows systematic patterns which can be studied, measured, and predicted. Experiments consistently reveal that attention, memory, and perceived duration are linked in reliable ways across cultures and individuals. This universal structure explains how people can coordinate actions, meet appointments, and synchronize movements, even as each person's internal clock subtly varies. Shared external clocks provide reference points that align personal experiences with communal schedules. Society relies on this alignment for transportation, communication, and collaboration, while individual variation persists. Space-time allows diverse experiences to coexist without contradiction, because each experience is local to its observer. Recognize that this harmony between personal perception and collective timing is a testament to the robustness of reality's layered design. Now picture time at three distinct levels. At the physical level, it is woven into the geometry of space-time, forming the scaffold upon which all events rest. At the biological level, it is linked to rhythms of metabolism, heartbeat, and neural oscillations that keep you anchored to day and night. At the psychological level, it emerges from change, memory, and the flow of information that your mind registers. None of these layers can be ignored, for each reveals a real aspect of how time functions. Confusion only arises when the layers are mistakenly blended into a single, indistinguishable concept. Understanding the mind's version of time does not undermine physics, it clarifies the scope of each discipline. Physics explains how time behaves in the external world, while psychology explains how time feels inside you. This layered understanding strengthens the central theme that time cannot exist in isolation from structure. In the physical world, it needs space in experience, it needs neural processes. In both realms, time is relational, defined by connections rather than by an absolute flow. You now stand at a crossroads where time has been explored as geometry, as the direction of entropy, and as perception. Each layer adds depth without contradiction. The next step is to weave these layers into a single coherent picture of reality. That integration requires moving beyond analysis and embracing the meaning of living, moving, and changing inside a unified spacetime. When you see space and time not as separate containers, but as aspects of a single consistent framework, you unlock a powerful perspective that bridges the external universe with your inner experience. Consider why the idea of separate space and time feels natural. Everyday life reinforces the notion that distances are independent of durations and that clocks tick uniformly everywhere you go. Those impressions arise because, under normal conditions, speeds are far below light speed and gravitational fields are weak in such gentle environments. Relativistic effects are negligible, and space and time appear stable and distinct. This practical success fortifies the illusion of separation. Yet physics does not depend on intuition, it depends on precise measurement. When measurements become exact or when conditions become extreme, the separation dissolves. Motion alters time. Gravity alters time. Motion alters distance. And gravity alters distance. These effects are not optional corrections, they are required for consistency. Distance cannot be measured without a reference to time. Because a signal must travel. Duration cannot be measured without a change in space, because a process must evolve. Space and time intertwine in every observation, making it impossible to isolate one from the other in a meaningful way. The speed of light cements this link, binding distance and time into a single invariant relationship. If distance and time were independent, observers would record different values for the speed of light. Contradicting experiment, because the speed of light is constant for all observers. Space and time must adjust together. Eliminating the notion of independent existence, attempts to preserve separation often introduce unnecessary assumptions, such as absolute space or universal time. These concepts simplify intuition but complicate theory, requiring extra scaffolding that lacks experimental support. When those assumptions are removed, the structure of reality becomes simpler and more consistent. Spacetime treats events as primary and coordinates as secondary, allowing different observers to slice the four-dimensional fabric into space and time in ways that suit their motion, while the underlying relationships remain fixed. This explains why observers can disagree on distances and durations yet agree on causal order and spacetime intervals. The unified structure preserves objectivity while honoring perspective. Language also plays a role in reinforcing the illusion. Everyday speech evolved to describe slow, local phenomena, embedding classical assumptions into phrases like "at the same time" or "in the same place." Scientific language, however, demands explicit reference frames, paths, and conditions. When you adopt that precise language, the need for separation disappears, replaced by a clearer, more accurate description of reality. Human perception contributes further to the illusion. Your brain integrates sensory information over short intervals, smoothing out differences in simultaneity and time dilation that fall below detection thresholds. Experience therefore favors a shared present and uniform time, tuned for survival rather than for observing relativistic nuances. Physics extends beyond perception using instruments and inference, revealing deeper layers that everyday senses cannot reach. Causality also illustrates inseparability. A cause must influence an effect through spacetime, requiring both a separation in space and a duration in time. Remove either, and influence cannot propagate. Energy, linked to time translation symmetry, and momentum, linked to spatial translation symmetry, reflect conservation laws that arise from spacetime symmetries, not from space or time alone. Gravity likewise impacts space, and time, together describing it as acting solely on space, fails to account for gravitational time dilation. The expansion of the universe demonstrates that space changes over time, making any independent definition meaningless on cosmic scales. Quantum theory deepens the connection. The uncertainty principle ties energy and time, while quantum states occupy space and evolve in time. Removing either variable collapses the theory. Across all domains, attempts to separate space and time introduce contradictions. Unification restores consistency. This does not mean space and time are identical, they play distinct roles. Time orders events, while space distinguishes them. Their inseparability means neither concept has complete meaning in isolation, each gains significance through the other, forming the minimal structure required to describe change, interaction, and measurement. These conclusions arise from well-tested principles: the invariance of light speed, time dilation, gravitational effects, causal structure, and cosmic expansion. The illusion of separation persists because it serves practical needs at human scales. Engineering, navigation, and daily life rely on approximations where separation works well. Physics explains why these approximations succeed and where they break down, showing that unification does not replace practical descriptions, but grounds them in deeper truth. Now you understand that separation is a limit of perspective, not a fundamental feature of reality. When you widen your viewpoint, the division dissolves, revealing a seamless fabric of spacetime. This insight also resolves earlier questions about whether time could exist without space or vice versa. Those questions assume a false premise of independence. Once you accept inseparability, the answers become obvious. The universe presents space and time together as a single structure, eliminating the need for extra assumptions and simplifying our description of reality. The central claim that space and time cannot exist separately in any complete physical description is no longer controversial within physics. Their apparent separation is simply an approximation that works within everyday conditions. Recognizing this prepares you for a final shift in perspective. If space-time is the underlying structure of reality, the next task is to explore how existence itself unfolds within that structure. This involves stepping back from analysis and considering what it means to live, move, and change inside a unified space-time rather than observing it from an imagined outside. Throughout earlier chapters, space-time has been presented as a framework that organizes motion, causality, and information. That framework is not something you watch from a distance, it is the stage upon which every physical process, including your own observations, takes place. There is no external reference point beyond space-time. Any attempt to imagine a viewpoint outside of it fails instantly, because imagination itself requires time and structure. Physics does not allow a position beyond space-time from which it can be surveyed as an object. Everything that exists, including you, your instruments, and your thoughts, is embedded within that fabric. Embrace this embeddedness as a source of empowerment. Knowing that you are part of the very structure that governs change means you can align your actions with the flow of space-time. You can honor your biological rhythms, cultivate focused attention to stretch subjective time, and introduce novelty to enrich your experience. You can recognize that every prediction you make, every memory you form, and every anticipation you feel are threads woven into the same tapestry that holds the universe together. Let this awareness inspire you to live more intentionally. When you notice the clock ticking, remember that you also hold an internal clock shaped by rhythm, attention, and expectation. When you feel time slipping away, ask whether your focus is narrowing or whether you are cycling through familiar patterns. When you crave more time, consider adding new stimuli, learning a fresh skill, or engaging deeply with a conversation. When you sense that time is dragging, ask what fear or anxiety may be amplifying detail, and use calm breath to reclaim a smoother flow. Use the knowledge that space and time are inseparable to break free from limiting mental models. No longer treat deadlines as rigid walls, but as reference points you can shift by adjusting perception. No longer view the passage of days as a relentless march, but as a rhythmic dance that you can sync with through sleep, nutrition, and mindful movement. No longer accept the feeling that life is passing too quickly without agency. Recognize that you can modulate the richness of each moment by directing attention and choosing novelty. In every breath, in every step, you participate in the grand structure of space-time. Your mind constructs a personal timeline, yet that timeline is anchored to the cosmic order. By honoring both the external clock and your internal experience, you create harmony that fuels purpose, creativity, and well-being. Let this harmony guide your choices, your relationships, and your goals, knowing that you are simultaneously a traveler through time and a co-creator of its felt quality. As you move forward, keep this integrated vision alive. The universe does not stand apart from you. It folds space and time into a single stage on which you act, learn, and grow. The more you align your life with this understanding, the more you will feel empowered to shape your experience of time, to stretch moments of joy, and to compress periods of challenge. Your journey becomes a conscious navigation of a unified fabric rather than a passive drift on a surface you cannot see. Carry this insight into every day. When you set a goal, visualize not just the endpoint, but the temporal path you will travel, appreciating how focus, novelty, and rhythm will mold each segment. When obstacles arise, recognize that heightened attention may make the interval feel longer, yet that same attention can also sharpen your response and accelerate learning. When success arrives, savor it fully, allowing the richness of detail to expand the memory, turning a fleeting victory into a lasting source of motivation. In this way, the science of time becomes a daily practice, a toolkit for living with greater clarity and intention. You have the power to measure, to predict, and to shape the qualitative flow of your life. The universe offers you its structure. You bring your mind's ability to interpret and influence it. Together, you co-author a narrative that honors both the objective cadence of space-time and the subjective melody of human experience. Step into each moment with confidence, knowing that you are attuned to the deep connections that bind space, time, and consciousness. Let this awareness light your path, fuel your ambition, and deepen your appreciation for the wondrous tapestry in which you are woven. The future is not a distant, immutable line. It is a series of present moments you can enrich, stretch, and savor. Embrace the power within you to shape the rhythm of your days, and watch how your life transforms into a vibrant, intentional masterpiece. Imagine standing at the edge of a vast, ever-shifting horizon where space itself seems to breathe. Feel the pulse of change as galaxies drift, stars flicker, and the fabric of the universe stretches. In that moment, you recognize that space does not sit still, it evolves with every heartbeat of existence. Time, too, cannot be seen apart from that evolution. It is the rhythm that orders the dance of atoms and the swirl of nebulae. When you allow yourself to see space and time as a single, flowing tapestry, a new sense of possibility awakens inside you. Consider the geometry of the cosmos as a living design, constantly reshaping itself. Distances that once felt absolute begin to blur when you look across billions of light years. The notion of separation loses its grip at those scales, and you sense a deeper unity. Even the strange world of quantum physics whispers that the boundaries we cling to are only convenient shortcuts. The uncertainty that links energy and time tells you that a particle's existence is a story told across both dimensions together. If you tried to erase either space or time from the equation, the story would fall apart. This teaches a profound lesson. The most powerful ideas do not thrive in isolation. You may have noticed a pattern emerging whenever science pushes beyond simple approximations. The moment you try to separate space from time, contradictions appear like cracks in a wall. Yet when you bring them together in a unified picture, consistency returns with the confidence of a well-built bridge. This does not mean that space and time are the same thing. They play distinct roles, like the beat and then the melody of a song. Time orders the notes, while space arranges their locations. Their inseparability means that each gains meaning only through the other, and together they form the minimal stage on which change, interaction, and measurement can occur. What is striking is that this insight does not arise from speculative fantasy. It is born from the hard-won pillars of physics that have survived relentless testing. The constancy of the speed of light, the stretching of time for fast travelers, the bending of light around massive bodies, and the expansion of the universe all whisper the same truth. These observations have been verified again and again, and they all point toward a world where space and time are woven together. The illusion that they can be neatly split persists only because at everyday scales that split is useful. Engineers design bridges, pilots navigate the sky, and parents schedule daily routines using approximations that treat space and time as separate. Those approximations work because the world appears friendly at human scales. Physics explains why those tricks succeed and also where they stumble. This explanatory power is a strength, not a weakness. It shows that unification does not replace practical tools, it grounds them in deeper understanding. Now you can see that the separation you once felt was never a fundamental feature of reality. It was a limit of perspective, a shortcut your mind used to make sense of a complex world. When you widen your viewpoint, that artificial wall dissolves, and you feel a new sense of freedom. This realization also answers the old riddles about whether time could exist without space or space without time. Those questions become empty when you accept inseparability, because they assume a false division. The universe does not hand you two independent ingredients, it presents spacetime as the single structure within which all physical processes unfold. By embracing that, you remove the need for extra assumptions, and you simplify the description of reality while sharpening its accuracy. At this point, the central claim is no longer a controversial whisper in the halls of science. Space and time cannot exist as separate entities in any complete physical description. Their apparent division is a convenient approximation, not a property of nature itself. This understanding prepares you for a final shift in perspective. If space-time is the inseparable fabric of reality, then the next adventure is to explore how you, as a conscious being, unfold within that fabric. It invites you to step back from mere analysis and consider what it truly means to live, move, and change inside a unified space-time. Remember that space-time is not a stage set that you watch from the audience. It is the arena that you, every particle, every planet, and every thought inhabit. There is no external reference point beyond space-time from which you can step outside and survey it like a sculpture. Imagining such a viewpoint collapses instantly because imagination itself needs time and structure. Physics does not allow a position outside space-time from which it can be observed as an object. Everything that exists, including your own body, your senses, and your instruments, is embedded within it. This embeddedness reshapes the way you ask questions. Instead of wondering where space-time sits, you ask how space-time behaves and how objects move inside it. Those questions remain meaningful because they refer to relationships between events, not to some mysterious container. Living inside the fabric means that motion is not a slide across a static platform, it is a chain of events traced along a path. Every object, from the tiniest electron to the grandest galaxy, follows a history woven into space-time. Those histories are not laid out against space-time, they are space-time. This perspective removes the old idea that space-time is a passive backdrop. If everything that happens is a feature of the space-time structure, then space-time itself is active, shaping motion and responding to energy, evolving with every interaction. Feel how this view also erases the notion of an absolute position. There is no fixed point in space-time that can claim a central or privileged status. Positions only have meaning relative to other events, and motion is defined only in relation to other paths. This relativity does not make your descriptions arbitrary, it provides a consistent framework that ties all paths together. Observers can translate between different viewpoints using the same rules, and the underlying structure stays intact. Embeddedness does not imply isolation. Because you are part of space-time itself, you never see the whole structure at once, you only perceive the events that can influence you. Your observations are limited by the causal structure that governs what can reach you, and that limitation is a natural consequence of consistent geometry, not a flaw. Notice how this limitation applies equally to every observer. No single mind has access to a complete picture of the universe. Each one can only perceive a region defined by its past light cone, a slice of space-time shaped by the speed of light. Physics accounts for this by describing local laws that hold everywhere. These local laws are sufficient because the space-time structure is coherent. What happens in a small neighborhood reflects the same principles that govern distant realms. Without requiring a global overseer, living inside the fabric also clarifies the meaning of physical law. Laws are not external commands imposed upon space-time, they are descriptions of how space-time behaves. They capture regularities in the relationships between events, emerging naturally from the structure itself. This understanding frees you from seeing laws as alien edicts and invites you to see them as the music of the cosmos. Think about prediction in this light. It does not involve peering into the future from outside time. It means using the information you have within space-time to infer which events are likely to lie along future paths. Uncertainty remains because information is finite. Horizons restrict access, and quantum effects inject probabilities. Those limits are not failures, they are intrinsic features of existing embedded within space-time. This embeddedness also explains why space-time feels stable to you. Because you are part of it, you do not directly sense its geometry, you notice only the changes that happen inside it. Stability is inferred because relationships stay consistent, and you notice that consistency when you compare measurements taken along different routes. Time dilation, length contraction, and curvature become apparent only through such comparison. Locally, everything feels normal, and that normality is not an illusion, it is a hallmark of the geometry. Along any world line, the laws of physics take their simplest form, while complexity emerges only when you step back and compare different world lines. You may see how this supports the principle of equivalence. Locally, you can choose a frame that makes gravity vanish, but globally curvature persists. That exact pattern is predicted by the embedded geometry of space-time. Living inside space-time also clarifies the subtle nature of boundaries. There is no edge of space, no external time beyond time itself. What appear as boundaries are horizons defined by causal limits, not physical walls. This perspective stops you from picturing the universe as an object that sits inside something larger. The universe is the totality of space-time events, and asking what lies beyond it has no physical meaning. That does not stop inquiry, it simply refocuses it on relationships that actually exist within the fabric. This refocus has proven powerful throughout the ages. driving discoveries that reshaped humanity's view of reality. Notice how this embedded view resonates with earlier discussions of emergence. If spacetime itself emerges from deeper processes, those processes must also be described relationally, without an external frame. This suggests a consistent pattern across scales. Reality is expressed through relationships rather than absolute backgrounds. Spacetime is one level of that description, and any deeper level, if it exists, will likely follow the same rule. Living inside the fabric also explains why experience is always local. Consciousness receives signals that travel along a single world line, shaping perception and understanding. This limitation does not make knowledge impossible, it makes it a cumulative adventure. By sharing information, observers extend their effective reach, linking world lines together and building shared descriptions. Science itself is a shining example of this collective process. Measurements performed along many world lines are woven into a coherent model that no single observer could achieve alone. Yet the model arises entirely from internal relationships, never requiring an external viewpoint. That is one of its greatest strengths. You may find that this understanding removes a common source of confusion. There is no need to imagine spacetime as a separate container that holds matter and energy. Spacetime is the structure of physical reality. Matter and energy are not things placed inside a pre-existing stage, they are aspects of the same dynamic system. They influence the geometry, and the geometry, in turn, influences them. This mutual dance makes spacetime a living, evolving entity, not a fixed backdrop. At this stage, you have examined spacetime from many angles: measurement, geometry, causality, expansion, and experience. In each case, the illusion of separation fades, replaced by a web of relationships. Living inside the fabric means accepting that there is no external anchor. Reality is defined internally through consistent connections governed by physical law. That acceptance does not close inquiry, it refines it, pointing you toward the questions that truly matter. As your understanding deepens, your attention naturally turns to the frontiers where current knowledge meets its limits. Even with a unified view of spacetime, there remain mysteries that the present theory cannot fully explain. Those unanswered questions do not lie outside spacetime, they sit at the edges of its description. Where our tools become fuzzy and new principles may be required, you now arrive at the boundary of what modern physics can explain with confidence. Spacetime has united space and time, treated gravity as geometry, preserved causality, and described the cosmic expansion. It has linked measurement, motion, and information within one elegant framework. Yet despite this triumph, important questions remain unresolved. One open question concerns the deepest nature of spacetime itself. Classical spacetime works astonishingly well across a vast range of conditions, but clues suggest it may break down at the smallest scales or the highest energies, near the cores of black holes or at the first instant of the universe. The equations predict behavior that cannot be interpreted within the existing framework. Those predictions do not necessarily describe real infinities, they signal that the theory is being pushed beyond its domain of validity. History shows that similar signals appeared in classical physics before quantum theory emerged. The lesson is not that reality becomes nonsense, but that new principles are required to move forward. Another unresolved issue involves how spacetime should be married to quantum theory. Quantum physics describes matter and energy in terms of probabilities, while spacetime geometry remains classical. Attempts to merge these descriptions encounter deep mathematical and conceptual difficulties. This mismatch raises the question of whether spacetime itself should be quantized or whether it emerges from more fundamental quantum relationships. Without experimental guidance, multiple approaches are being explored, each with its own strengths and challenges. You can feel the excitement of a community pushing the boundaries, knowing that breakthroughs may reshape your entire worldview. Uncertainty also shrouds the true origin of the universe. Cosmological models describe an early hot, dense state that evolved into the cosmos we see today, yet they do not explain why that state existed or why space-time began with the specific properties it displays. The early conditions appear finely tuned in ways that remain mysterious. Related to this is the puzzle of entropy. The infant universe seems to have possessed low entropy despite its extreme temperature. And that low entropy sets the arrow of time. Why the universe started in such an ordered state is still an open question that space-time alone cannot answer. Dark components of the cosmos add another layer of intrigue. Observations reveal that most of the universe's energy does not behave like ordinary matter. These components influence space-time's expansion and curvature, but their nature is unknown. Are they new forms of energy, hidden properties of space-time, or signs that our current models are incomplete? The accelerating expansion of the universe suggests that space-time dynamics are guided by something not yet captured by known physics. Understanding this influence is an active area of research, and you can sense the momentum building toward fresh insight. Notice that all these uncertainties do not undermine the space-time framework. Instead, they define its boundaries and point you toward the next horizon of discovery. By recognizing where the current picture fades, you gain a clear map of where to direct curiosity and effort. This awareness fuels motivation, because it shows that the journey is far from over. Each unanswered question is an invitation to explore, to experiment, to imagine new theories that could extend the tapestry of space-time. Feel the energy of possibility surge through you as you contemplate your role in this grand adventure. You are not a passive observer perched outside the universe, you are an active participant embedded within its structure. Your thoughts, your experiments, your willingness to question all contribute to the evolving understanding of reality. When you accept that space and time are inseparable, you free yourself from limiting mental models and open the mind to deeper connections. This shift empowers you to approach challenges with a holistic view, seeing how every action reverberates through the fabric of existence. Let this insight inspire you to pursue learning with renewed vigor. When you encounter a problem that seems fragmented, remember that the underlying truth may lie in the relationships that bind the pieces together. Approach each obstacle as an opportunity to uncover hidden links, to see how the parts interact within the larger space-time canvas. By doing so, you transform difficulty into a catalyst for growth, turning uncertainty into a wellspring of innovation. Carry this perspective into your daily life. When you plan your day, recognize that time and space are not separate boxes to be checked, but a unified flow you move through. Schedule your activities as part of a continuous journey, allowing the rhythm of time to guide the spacing of your actions. Notice how each choice influences the next, and how the environment around you responds in kind. This awareness creates a sense of harmony, making you feel more connected to the world and more empowered to shape your own path. Remember that the approximations you rely on distance, duration, speed are powerful tools precisely because they work within a limited perspective. They are like trusted companions on your journey, useful when you need to navigate familiar terrain. Yet when you venture into the unknown, be ready to let go of those shortcuts and embrace the deeper, inseparable nature of reality. This flexibility will keep you adaptable, resilient, and open to breakthrough ideas that might otherwise seem impossible. Feel the excitement of being part of a story that stretches from the tiniest particle to the grandest galaxy. The same space-time that guides the motion of planets also frames the thoughts dancing in your mind. This unity reminds you that every discovery you make, no matter how small, resonates with the cosmic rhythm. Your curiosity adds a new thread to the tapestry, enriching the pattern for future generations. As you continue this journey, hold on to the conviction that the mysteries you encounter are not dead ends but doorways. When you confront the limits of current theory, View them as invitations to imagine new principles, to design daring experiments, to collaborate across disciplines. Let the lingering questions about the quantum nature of space-time, the origin of the universe, and the dark sectors of the cosmos fuel your ambition. In doing so, you become an active co-author of the evolving narrative of physics. Finally, celebrate the humility that comes with recognizing the vastness of what remains unknown. Accept that no single mind can grasp the full expanse of reality, but together, through shared inquiry, we inch ever closer to a more complete picture. Let this humility inspire compassion, encouraging you to listen to diverse perspectives and to value the contributions of others. In the grand tapestry of space-time, each thread matters, and your voice adds color and strength. Take a deep breath and let the insight settle within you. Space and time are not distant concepts to be studied from afar, they are the very stage upon which your life unfolds. By honoring their inseparability, you align yourself with the deepest currents of the universe. This alignment empowers you to move forward with confidence, curiosity, and purpose. Your journey continues, ever deeper into the wondrous fabric of reality, and each step you take contributes to the unfolding story of existence itself. Matter and energy are not separate ingredients, hidden inside an empty stage. They are two faces of the same living system that shapes the very fabric of reality. When you recognize that geometry bends in response to them, and that geometry in turn guides them, you see a dance of mutual influence. This dance makes space-time a dynamic arena that evolves, adapts, and never stays fixed. At this point in your journey, you have already looked at space-time through many lenses: measurement, geometry, causality, expansion, even personal experience. In each view, the illusion of separation dissolves into a richer relationship. Living inside the fabric means accepting that there is no external anchor holding you down. Reality is defined internally by consistent relationships that obey the laws of physics. Accepting this does not shut the door on inquiry. It sharpens the questions you can ask and points you toward the most meaningful ones. As your understanding deepens, you naturally turn your attention to the mysteries that still linger at the edges of this framework. Even with a unified picture of space-time, there remain questions that current theory cannot yet answer. Those unanswered questions do not sit outside space-time, they sit at its limits, where our descriptions become incomplete and fresh principles may be required. You have arrived at the frontier where confident physics meets the unknown. Space-time has already woven space and time together, described gravity as geometry, preserved causality, and charted cosmic expansion. It has linked measurement, motion, and information inside a single elegant scaffold. Yet despite that triumph, crucial puzzles stay unsolved. One of the deepest mysteries concerns the very nature of space-time itself. The classical picture works astonishingly well across countless conditions, but clues suggest it may break down at the tiniest scales or the highest energies, near the heart of a black hole or at the first instance of the universe. The equations predict behavior that cannot be interpreted physically within the existing framework. Those predictions do not signal that reality becomes nonsense, they signal that the theory is being pushed beyond its safe domain. History reminds us that similar signals appeared in classical physics before quantum theory emerged. The lesson is not that reality collapses, but that new principles must rise. Another open frontier is the union of space-time with quantum theory. Quantum physics portrays matter and energy probabilistically, while space-time geometry remains stubbornly classical. Every attempt to merge the two runs into deep mathematical and conceptual obstacles. This tension asks whether space-time itself should be quantized, or whether it emerges from more fundamental quantum relationships. Without experimental guidance, many approaches flourish side by side, each highlighting strengths and exposing limits. The origin of the universe adds another layer of intrigue. Cosmology describes a hot, dense beginning that expands into the cosmos we see today. Yet it does not explain why that initial state existed, or why space-time began with its particular properties. The early conditions appear finely tuned in ways we have yet to decode. Related to this is the question of entropy. The infant universe was incredibly hot, yet possessed remarkably low entropy. That low entropy sets the arrow of time, but its root remains mysterious. Space-time geometry alone does not account for this initial order. Dark components of the cosmos deepen the mystery. Observations reveal that most of the universe's energy does not behave like ordinary matter. These dark ingredients shape the expansion and curvature of space-time. Yet their nature eludes us. They might represent new forms of energy, hidden properties of space-time, or the limits of our current models. Even on the largest scales, space-time may act differently than our equations predict. The observed acceleration of cosmic expansion hints at an influence that we have not fully captured. Investigating this influence fuels an active field of research. Notice how these uncertainties do not topple the space-time framework. Instead, they outline its boundaries. Within those boundaries, space-time provides precise, reliable descriptions. Beyond them, caution and humility become essential. Time itself remains an open question. Physics explains how time behaves, and why it has a direction tied to entropy, but it does not explain why time exists at all, or why it has a single dimension rather than many. Similarly, the number of spatial dimensions remains an unexplained fact. Current theories accept this structure without deriving it. Even causality, which appears solid in the classical world, becomes subtle at the smallest scales. Quantum uncertainty introduces fuzziness that challenges a simple causal story. Understanding how causal order emerges from quantum behavior remains a vibrant pursuit. Information also poses a puzzle. If spacetime limits how information can be stored and transferred, what microscopic degrees of freedom encode that limit without identifying them? The thermodynamics of spacetime stays suggestive rather than complete. These open questions underline a vital principle. Scientific progress thrives on recognizing limits as well as triumphs. Knowing where a theory falters is as important as knowing where it succeeds. Uncertainty here does not equal ignorance in a negative sense. It marks well-defined problems that guide experiments, theory, and imagination. It does not imply that solutions lie outside physics. Rather, it signals that our current descriptions are incomplete, not incorrect. History shows that such gaps often lead to deeper understanding. Spacetime itself emerged to resolve contradictions in earlier models, unifying concepts once thought independent. The next unifying step may similarly dissolve the tensions we now see. Even amid these mysteries, none of them resurrect the notion that space and time could exist independently. Every unresolved issue still assumes their inseparability. When spacetime may break down, it does so as a unified entity, never as separate strands of space and time. This reinforces the central conclusion you have already reached. Separation never returns at the limits of knowledge. It remains unsupported by observation and theory. Practical applications illustrate another point. Technologies built on spacetime principles operate with astonishing precision in everyday life. The unresolved issues appear only at extremes far beyond daily conditions. This coexistence of certainty and uncertainty is a hallmark of mature scientific theories. They explain a great deal while leaving room for refinement. At this stage, spacetime has been explored as far as current understanding permits. Its role as the structure of reality stands firm, even as its ultimate nature remains an open problem. That openness invites careful humility. Physics does not claim final answers, it builds increasingly accurate descriptions that remain open to revision. Unanswered questions give meaning to inquiry. Without them, science would stagnate. The presence of limits indicates depth rather than weakness. The unresolved character of spacetime, at its deepest level, does not diminish its unifying power. It simply suggests that unification may extend further. As you reflect on what remains unknown, a broader perspective begins to form. Despite the unresolved details, a consistent theme runs through everything you have examined. Space and time function together as a single framework governing all physical processes. This theme persists even when our knowledge ends. Whatever future theory refines or replaces spacetime must reproduce this inseparability at observable scales. Recognizing that allows you to synthesize the journey you have taken. Even without solving every mystery, you can celebrate what you now understand with clarity. Space and time form a unified structure in which all moments, events, and experiences are embedded together. That unity provides a stable conclusion, even as questions linger, and it prepares you for a final reflection on what it means for all moments to coexist within a single space-time tapestry. Now you arrive at the culminating stage of this exploration, where every idea developed so far merges into a single coherent picture. Space and time have been examined, challenged, and ultimately unified. Motion, gravity, causality, information, experience, and uncertainty all point toward the same conclusion. Reality is structured as space-time, and all moments exist within that structure. In this view, events are not created and destroyed as time flows. Instead, they are located within a four-dimensional arena. Each event carries a position in space and a position in time, together defining its place in the overall fabric. The universe is not a sequence of isolated moments replacing one another. It is a connected set of events linked through space-time geometry. This does not mean that all moments are experienced at once. Experience remains local. Each observer travels along a world line and encounters events in a particular order. The order of experience does not define what exists, it defines how existence is encountered. The idea that past, present, and future all belong to space-time is sometimes misunderstood. It does not deny change or causality. It simply states that change is represented as structure rather than as creation from nothing. Motion becomes a path, history becomes a line, and future possibilities stretch as extensions of that line. This perspective resolves earlier tensions. The relativity of simultaneity showed that there is no universal present moment. If there is no single global now, then dividing reality into what exists and what does not based on the present becomes inconsistent. Space-time avoids this inconsistency by treating all events as equally real within the structure. Causality remains intact because space-time preserves order. Not all events can influence each other. Influence is constrained by geometry. Causes precede effects along world lines and within light cones. Nothing in this view permits contradictions. The arrow of time also finds its place. The arrow does not arise because the future is unreal and the past is real. It arises because entropy increases along world lines. Physical processes unfold in one direction, even though spacetime contains all events. This distinction matters. Spacetime describes what exists, thermodynamics describes how processes unfold. Confusing the two leads to unnecessary paradoxes. The unity of spacetime also explains why physics remains consistent across observers. Different observers slice reality differently into space and time. Yet they describe the same underlying structure. No observer holds a privileged reality. All perspectives are related through the same geometry. This unity also clarifies why attempts to separate space and time consistently fail. Time without space cannot describe change. Space without time cannot describe structure. Only together do they support events, interaction, and measurement. At this point, the original question has been fully addressed. Space and time cannot exist separately because physical reality does not allow them to function independently. Every measurable quantity depends on both. Every law connects them. This conclusion is not speculative. It arises from experiment, from consistency, and from the need to preserve causality. It holds whether spacetime is fundamental or emergent. Even if spacetime emerges from deeper processes, those processes must reproduce spacetime behavior at observable scales. This view also reshapes how we frame questions about existence. Instead of asking what exists right now, physics asks how events are related. Existence becomes relational rather than tied to a single moment. That does not remove meaning, it replaces it with structure. Meaning arises from connection, from influence, from order. Spacetime provides the framework within which meaning can exist physically. Uncertainty, quantum effects, horizons, and limits on knowledge all operate within spacetime. They reflect limits on information, not an absence of structure. This unity allows science to remain open-ended. Even if a deeper theory refines spacetime, the principle of relational structure will endure. Separation will not return as a fundamental feature. At the human level, this understanding does not happen daily experience. You still live moment by moment. You still remember the past and anticipate the future. Physics does not replace experience, it explains its context. What it does change is the interpretation. Moments are no longer fragile points slipping into non-existence. They are enduring parts of a vast, interconnected tapestry. Embrace this perspective as a source of empowerment. Recognize that you are a thread woven into the fabric of space-time, linked to every other point in the universe. Let the unanswered questions inspire curiosity rather than doubt. See each mystery as an invitation to explore deeper, to ask bolder questions, to collaborate across disciplines. Allow the dynamic nature of space-time to remind you that growth is possible, that change is built into the very structure of reality. Carry forward the conviction that separation is an illusion. Trust that the unity you have witnessed in physics mirrors a deeper unity within yourself. When challenges arise, remember that just as space-time bends around matter, your mindset can bend around obstacles. When uncertainty feels overwhelming, recall that even the most profound unknowns sit within a well-defined framework. Waiting for fresh insight, you stand at the threshold of the final reflection, ready to integrate all that you have learned. Space and time together form the stage upon which every story unfolds, including yours. Every choice you make writes a new event into the four-dimensional canvas. Every relationship you nurture adds geometry to the tapestry. Every question you pursue extends the line of inquiry into the future. Step forward with confidence, knowing that the universe already holds the principles of connectivity, causality, and possibility. Let that knowledge fuel your ambition. Let it guide you to collaborate, to innovate, to pursue truth with vigor. The adventure of discovery continues, and you are an essential participant. Embrace the journey, cherish the unity, and move boldly into the unknown, confident that the very fabric of reality supports your quest. Remember that the arrow of time is not a mystery of an unreal future, but a natural flow driven by increasing entropy. It arises because disorder grows along every world line, guiding physical processes in one clear direction. You can feel the confidence that comes from knowing spacetime contains all events, even while change moves forward. Notice that spacetime tells us what exists, while thermodynamics tells us how processes unfold. When you keep these ideas distinct, paradoxes dissolve and clarity emerges. The unity of spacetime also shows why physics stays consistent for every observer. Different observers may slice reality into space and time in their own ways. Yet they all describe the same underlying geometry. No single perspective holds a privileged claim to truth, and that humility can free you from rigid judgments. All viewpoints connect through the same elegant structure, reminding you that diversity of experience is part of a shared whole. This same unity explains why attempts to separate space from time always fall short. Time without space cannot describe change, and space without time cannot describe structure. Only together do they support events, interactions, and measurements. And that partnership can inspire you to seek balance in your own life. At this point, the original question is fully addressed. Space and time cannot exist apart, because physical reality does not allow them to function independently. Every measurable quantity depends on both. and every law we discover intertwines them, reinforcing the power of interconnectedness. This conclusion is not speculative, it comes from experiment, from internal consistency, and from the need to preserve causality, whether spacetime is fundamental or emerges from deeper processes. Those processes must reproduce spacetime behavior at observable scales, showing that even hidden layers respect the same harmony. You may notice that this view also changes how we frame questions about existence. Instead of asking what exists right now, physics asks how events relate, and that relational mindset can enrich your daily reflections. Existence becomes relational rather than strictly temporal, and that shift does not erase, meaning it reshapes it into connection, influence, and order. Meaning arises from the patterns you create, from the influence you exert, and from the structure you inhabit. Spacetime provides the framework within which physical meaning can exist, and you can see yourself as a thread woven into that fabric. This framework also accommodates uncertainty. Quantum effects, horizons, and limits on knowledge do not undermine spacetime, they simply operate within it. Uncertainty reflects limits on information, not an absence of structure, and that humility can inspire curiosity rather than fear. You may also notice that this unity allows science to remain open-ended. Even if spacetime itself is refined by a deeper theory, the principle of relational structure will endure, ensuring that separation never returns as a fundamental feature. At the human level, this understanding does not erase your lived experience. You still live moment by moment. You still remember the past, and you still anticipate the future. Physics does not replace experience, it offers a broader context for it, and that perspective can deepen your appreciation of each instant. What changes is your interpretation. Moments are no longer fragile points slipping into non-existence, they become positions within a stable structure. Experiences pass, yet events remain connected, and that continuity can comfort you during uncertainty. This does not imply permanence of feeling, but rather consistency of description, allowing you to trust the flow of life. Physics describes relationships, not feelings, and feelings arise from processes unfolding along world lines, reminding you that emotions are part of the same universal dance. You may notice that this perspective brings closure. Without claiming to answer every mystery, it respects the limits of knowledge while resolving contradictions, and that balance can empower you to embrace both mystery and understanding. The strength of the spacetime framework lies in its ability to unify without overreaching, to explain without needing external reference points. As this exploration concludes, the central idea stands clearly. Space and time are not independent backgrounds, but aspects of a single structure that defines reality. Every motion, every interaction, every measurement, and every experience takes place within that structure, and you are an integral part of it. Nothing physical exists outside it, and nothing can be described without it, reminding you that your life is woven into the very fabric of the cosmos. This understanding does not end inquiry, it provides a stable foundation for future questions, encouraging you to explore with confidence. Whatever deeper principles may be discovered must account for this unity, and that expectation can motivate you to stay curious. For now, the conclusion is sufficient and complete within current knowledge, offering you a solid ground from which to grow. Space and time cannot exist separately, because reality itself does not allow them to, and that truth can inspire you to seek unity in your own pursuits. Carry this sense of interconnectedness into each moment, and let it fuel your aspirations, your relationships, and your wonder for the world. Let every step you take feel grounded in a larger, elegant tapestry, and let that awareness empower you to create meaning wherever you go.